Start of script. In the silent, unending night of space, a billion miles from the only home we have ever known, a magnificent golden eye has opened. It does not blink, it does not sleep, it stares, unblinking, into the deepest recesses of time, capturing whispers of light from the very dawn of creation. This is the James Webb Space Telescope, humanity's most ambitious emissary to the cosmos. It was built with a promise to show us our origins, to unveil the first stars, to confirm the grand, elegant story we had so carefully written for our universe. But a strange and unsettling narrative is beginning to unfold. The photons gathered by its gilded mirror are not just telling a story, they are whispering of a revolution. A quiet tremor is running through the halls of astrophysics, a feeling that mixes profound excitement with a deep intellectual vertigo. The discoveries being beamed back across the void are so strange, so unexpected, so powerful, that they are forcing us to question the very foundations of our cosmic understanding. And so, we must ask the question that hums beneath the surface of every new data release. Why does it seem that NASA and the entire scientific community is grappling with a sense of terror in the face of what the James Webb Telescope is finding? This is not the terror of a monster lurking in the dark. It is a far more profound and existential unease. It is the terror of the artist who finds the canvas is infinitely larger than they ever imagined. It is the terror of the historian who discovers a magnificent, fully formed civilization where maps insisted there should only be dust and echoes. It is the fear that our beautiful, painstakingly constructed model of the universe, the culmination of a century of genius, might be profoundly, fundamentally incomplete. The story of this terror begins not in the cold of space, but in the fires of human ambition. For decades, the Hubble Space Telescope was our window to the sublime. It gave us the pillars of creation, the Hubble Deep Field, and a universe teeming with galaxies. Hubble showed us a cosmos of breathtaking beauty, but it also showed us its limits. Like a ship that can only sail so far from shore, Hubble could not pierce the deepest fog of time. The universe is expanding, a discovery that reshaped all of human thought. This expansion stretches everything within it, including light itself. Light from the most distant, and therefore the most ancient, objects has been stretched on its 13 billion year journey to us. Visible light becomes infrared light, a form of energy our eyes cannot see, and which Hubble was not primarily designed to capture. The dawn of the universe was thus veiled from us, hidden behind a curtain of red-shifted light. To see this ancient era, we needed a new kind of eye, an eye that could perceive the infrared universe, the realm of cosmic dawn, and it would have to be colossal. To collect the faint, time-worn photons from the edge of existence, it would require a mirror of unprecedented size. This was the genesis of the James Webb Space Telescope. A project so audacious, so technologically demanding, that it teetered on the brink of cancellation for years. Its primary mirror, a breathtaking mosaic of 18 hexagonal, gold-coated beryllium segments, spans over 6.5 meters. A work of art designed to capture the universe's oldest secrets. But to see in the infrared, the telescope itself must be unimaginably cold. Warmth is the enemy, as any heat from the observatory would blind it. Like trying to take a photograph of a candle from inside a bonfire, it needed to operate at a staggering -233 degrees Celsius, just a few dozen degrees above absolute zero, the theoretical point where all atomic motion ceases. To achieve this, engineers devised one of the most complex structures ever sent into space, a 5-layered sunshield, the size of a professional tennis court. Each layer, thinner than a human hair, is made of a specialized material called kapton, coated in aluminum and silicon, designed to reflect the sun's ferocious heat back into space. The temperature difference from the sun-facing side to the perpetually shaded side of the shield is over 300 degrees Celsius, an almost unbelievable feat of thermal engineering. The journey to its final destination was a ballet of terrifying precision. Launched on Christmas Day, 2021, it embarked on a month-long, million-mile voyage. to a unique point in space known as the second Lagrange point, or L2. This is a place of gravitational stability, where the pull of the Sun and the Earth balance perfectly, allowing the telescope to orbit the Sun in lockstep with our planet, keeping its vital sunshield perpetually positioned to block heat and light. During this journey, hundreds of single points of failure had to work flawlessly. The unfolding of the sunshield, the deployment of the secondary mirror, the meticulous alignment of the 18 primary mirror segments to a precision of nanometers. It was the most complex deployment sequence ever attempted. The world watched, holding its breath. And it worked. It worked perfectly. The eye had opened. And humanity waited for the first images, expecting to see a more detailed version of the universe we thought we knew. What we got instead was the beginning of a cosmic revolution. To understand the shockwave that Webb sent through cosmology, we must first understand the story we used to tell ourselves. This is the standard model of cosmology, known as lambda-cold dark matter, or lambda CDM. It is a powerful and elegant narrative, built on decades of observation and theory. It begins with the Big Bang, approximately 13.8 billion years ago. The universe was an infinitely hot, infinitely dense singularity. It exploded outward, and in the first few minutes, the fundamental forces and particles took shape. For the first 380,000 years, it was a searing, opaque plasma of protons and electrons. Then, as it cooled, atoms formed and light was set free. This is the cosmic microwave background radiation, the afterglow of creation, which we can still detect today. The universe was then plunged into the cosmic dark ages. There were no stars, no galaxies, only vast, roiling clouds of hydrogen and helium gas, and the invisible scaffolding of dark matter. According to the lambda CDM model, gravity is a patient, slow artist. Over hundreds of millions of years, it began to gently pull these primordial gases together. The first stars, known as population 3 stars, would have ignited. These were predicted to be monstrous, hundreds of times the mass of our Sun, forged from pure hydrogen and helium. They would have lived fast and died young, exploding in cataclysmic supernovae that seeded the cosmos with the first heavy elements. From these ashes, the first galaxies would have slowly, painstakingly begun to form. Our models predicted these proto-galaxies would be small, clumpy, and irregular. Think of them as cosmic hamlets, not grand celestial cities. They would have been chaotic knots of gas and a few primitive stars. The grand, majestic spiral galaxies like our own Milky Way, or the elegant elliptical galaxies we see nearby, would take billions of years to form through a long, violent process of mergers and acquisitions as these smaller proto-galaxies collided and coalesced over cosmic eons. This was the established timeline, a slow, bottom-up process of cosmic construction. It was a story that made sense, and it was the story Webb was built to confirm. The telescope was designed to find these faint, messy, infant galaxies, the cosmic building blocks, in the first 500 million years after the Big Bang. Then, in the summer of 2022, the first deep field images were released. And the universe that Webb revealed was not the one we were expecting. Staring back at us from the dawn of time were galaxies that had no right to exist. In a patch of sky that to the naked eye is no larger than a grain of sand held at arm's length, Webb found galaxies shining just 300 to 400 million years after the Big Bang. This was already pushing the timeline, but the true shock was not their existence, but their nature. They weren't small, clumpy, or irregular. They were magnificent. Some appeared to have distinct disk structures, the beginnings of spiral arms. Spectroscopic analysis revealed they were already enriched with heavier elements, like oxygen and carbon, the very elements forged in the hearts of stars and essential for life. Imagine being an archaeologist who has a well-established theory that the first human settlements were simple mud huts, taking thousands of years to evolve into villages. Then, on your very first dig into the most ancient layer of Earth, you don't find mud huts. You find the foundations of a skyscraper. You find evidence of complex metallurgy and sophisticated infrastructure. This is the scale of the shock that astronomers felt. The discovery of galaxies like GLASS, Z13, and JADES GSZ130 was staggering. These were not cosmic hamlets. They were already bustling metropolises, shining with a maturity that our models said was impossible for that early epoch. The timeline simply doesn't seem to work. Where did the time come from for these galaxies to form such ordered structures? How did they accumulate so much mass so quickly? How did they manage to ignite such furious bursts of star formation and then enrich themselves with heavy elements in what amounts to a cosmic blink of an eye? It's like finding a fully grown redwood tree just 1 year after the seed was planted. The physics, as we understand it, requires a much longer period of gradual growth. And at the heart of this enigma lies an even more profound mystery: supermassive black holes. We now know that virtually every large galaxy, including our own Milky Way, has a supermassive black hole at its core, millions or even billions of times the mass of our Sun. The prevailing theory was that these monsters grew over time, starting as smaller black holes from collapsed stars and slowly feeding on gas, dust, and other stars, gradually swelling to their immense sizes over billions of years. But Webb is finding evidence of colossal black holes, already 1 million times the mass of the Sun, in the very earliest galaxies. These ancient quasars, the bright beacons powered by matter, spiraling into these black holes, are shining far earlier than they should. There is simply not enough time in the early universe, according to our models, for a black hole to grow that large, that fast. It's a cosmological crisis. It's like arriving at a party just 5 minutes after it started and finding someone has already managed to drink an entire swimming pool's worth of punch. It defies the known rates of consumption. This has forced scientists to scramble for new explanations. Perhaps the seeds of black holes weren't from single stars, but were formed from the direct collapse of unimaginably vast clouds of primordial gas, creating massive primordial black holes in the universe's first moments. Or perhaps there is some exotic, unknown physics that governs the growth of black holes, allowing them to feed far more efficiently than we ever believed possible. The textbook is being frantically rewritten in real time with every new dataset from Webb. This fundamental challenge to the timeline of cosmic evolution is the core of the scientific terror. It's the dawning realization that the Lambda CDM model, while incredibly successful at explaining the later universe, may be failing us at the very beginning. It's like having a brilliant biography of an adult that turns out to be completely wrong about their childhood. This doesn't mean the Big Bang is wrong, but it strongly suggests that the subsequent chapters, the story of how we get from the primordial soup to the first grand galaxies, is missing entire pages, or perhaps the entire volume needs a new author. The universe, it seems, was in a shocking hurry to get interesting. It was building complex structures far faster, far more efficiently, and far earlier than our most sophisticated simulations ever predicted. But the telescope's unnerving revelations are not confined to the dawn of time. It is also turning its golden eye to worlds much closer to home, planets orbiting other stars within our own galaxy. And here, too, it is rewriting what we thought was possible. For centuries, these exoplanets were just theoretical points of light, their existence inferred through the subtle dimming of their parent star as they passed in front, or the gentle wobble they induced. Webb has the extraordinary power to do something new, to perform atmospheric reconnaissance on these alien worlds. As an exoplanet transits its star, a tiny fraction of the starlight passes through its atmosphere. Within that light are the chemical fingerprints of the gases present in that world's air. Webb is a master codebreaker, capable of reading these spectral barcodes. One of its first targets was a hot Jupiter called WASP 39b. Scientists expected to find water, perhaps some sodium and potassium. What they found instead was the first definitive detection of carbon dioxide in an exoplanet's atmosphere, along with a host of other chemical surprises, including a strong signature for sulfur dioxide. This was a molecule they did not expect, and its presence hinted at active photochemistry, a process where starlight breaks down molecules, creating new ones. It told a story of a dynamic, active atmosphere, a chemical laboratory on a planetary scale. It was a proof of concept that sent ripples of excitement through the astrobiology community, because if Webb can analyze the air of a gas giant 700 light-years away, it can eventually analyze the air of a rocky, Earth-sized world orbiting in its star's habitable zone. And this is where a different kind of existential awe, a different shade of terror, begins to creep in. Webb is systematically sniffing the air of the TRAPPIST. One system, a star just 40 light-years away with at least 7 rocky planets, several of which orbit in the zone where liquid water could exist. For the first time in human history, we have a tool that could plausibly detect a biosignature. This is the faint, telltale sign of life, a chemical imbalance in an atmosphere that could only be sustained by biological processes. On Earth, the abundance of oxygen and methane is a direct consequence of life. Finding a similar combination on a distant world would be the single most profound discovery in the history of science. The terror here is the terror of the threshold. We stand at the precipice of an answer to the oldest question we have ever asked. Are we alone? If Webb finds nothing, decade after decade, on world after world, the silence from the cosmos becomes a deafening and lonely roar. It would deepen the Fermi paradox and force us to confront the possibility that life is terrifyingly rare. But if it finds something, if it detects the chemical signature of a biosphere on another world, our entire perception of our place in the universe shatters forever. The philosophical and societal implications are almost too vast to contemplate. The discovery would not be of little green men, but of a chemical spectrum on a computer screen, yet it would represent contact of a kind. A confirmation that the universe is not sterile, but seeded with potential. And Webb is the first machine we have ever built that could genuinely deliver that answer. The weight of that potential discovery is immense. Even when it looks at objects we thought we knew well, Webb unveils layers of complexity that leave us stunned. It turned its gaze to the iconic pillars of creation, the subject of Hubble's most famous photograph. Hubble showed us majestic towers of gas and dust, a celestial sculpture gallery. Webb, seeing in the infrared, pierced through the dust, and what it revealed was astonishing. Within the pillars, hundreds of newly forming stars, glowing bright crimson, were unveiled for the first time. These are protostars, still wrapped in their cocoons of cosmic dust, objects that were invisible to Hubble. Webb showed us the process of stellar birth with an intimacy and clarity that was unimaginable before. It showed us the intricate feedback loop, how the intense radiation from the massive, young blue stars at the top is simultaneously eroding the pillars away, while also triggering new waves of star formation within them. It transformed a static celestial photograph into a dynamic, violent, and beautiful cosmic nursery. Closer still, in our own solar system, it has rendered the familiar alien and new. Its portrait of Jupiter is a masterpiece of atmospheric dynamics. It captured the swirling chaos of the Great Red Spot, the delicate, ephemeral rings of the gas giant, and most hauntingly, the colossal, shimmering auroras at its poles. These auroras, far more powerful than Earth's northern lights, were seen in unprecedented detail, a ghostly dance of light larger than our entire planet. It showed us the weather on a world 1,000 times the volume of our own. It even captured the faint glow of the rings of Uranus and Neptune with a clarity we haven't seen since the Voyager flybys decades ago. It proves that even in our own backyard, there are profound discoveries waiting to be made, secrets hidden in plain sight, waiting for the right kind of eye to see them. So, we are left with a universe that is both grander and more perplexing than before. A universe that builds its most magnificent structures in a bewildering rush. A universe whose planetary atmospheres are complex chemical laboratories. A universe whose stellar nurseries are more violent and more fertile than we had imagined. Each discovery seems to break a rule or accelerate a timeline, and this forces scientists into a deeply uncomfortable but thrilling position. they must now entertain ideas that were once on the fringes of cosmological thought. One of the most significant tensions in cosmology today is the Hubble tension. Measurements of the universe's expansion rate using local, nearby objects give a different value than measurements based on the early universe's cosmic microwave background. It's a fundamental disagreement, and it hints that our lambda CDM model is missing a key ingredient. Webb's data on distant supernovae and galaxies will provide crucial new data points in this debate. If Webb confirms this discrepancy, it might mean we need to revise our understanding of dark energy, the mysterious force accelerating cosmic expansion, or even consider new physics from the universe's earliest moments. The sheer efficiency of early galaxy formation has led some researchers to dust off more radical ideas. Could the Big Bang have been more of a big bounce? Could our universe have emerged from the collapse of a previous one, inheriting some of the structure and black holes from its parent cosmos? This would help explain the shocking maturity of early galaxies, as they wouldn't be starting from scratch. These are highly speculative notions, but Webb's data is forcing them back into the conversation. The telescope is not just a tool for observation, it is an agent of theoretical chaos, demolishing old certainties and creating a fertile ground for new, bolder ideas. This is the true nature of the terror NASA faces. It is the terror of paradigm shift. Science progresses through the patient accumulation of data, but it leaps forward through revolution when a piece of evidence arrives that is so powerful it shatters the existing framework. Copernicus terrified the establishment by moving the Earth from the center of the universe. Galileo's telescope revealed moons orbiting Jupiter, terrifying those who believed all things orbited the Earth. Einstein's relativity terrified the classical physicists by showing that space and time were not absolute. The James Webb Space Telescope is the instrument of the next great scientific upheaval. It is showing us that the universe is not just more complicated than we imagine. It may be more complicated than we times imagine with our current models. The human story behind this is one of immense courage. Thousands of scientists and engineers dedicated their entire careers to this single machine. They poured their lives into a high-stakes gamble, a golden eye that might have failed in 1,000 different ways. Now, they are being rewarded with a data stream so rich, so revolutionary, that it is overwhelming their ability to process it. They are like explorers who set out to map a new island and have instead discovered an entire, unimagined continent. The work is exhilarating, but it is also daunting. Every new image contains a dozen new mysteries. Every spectrum contains a chemical puzzle. The very instrument of their triumph is the source of their profound new uncertainty. What does the future hold? The James Webb Space Telescope is just beginning its mission. It has a planned lifespan of over a decade, perhaps 2. It will continue to push further back in time, hunting for the mythical population 3 stars, the true first light of the cosmos. It will systematically survey the atmospheres of dozens of Earth-like exoplanets, playing the greatest lottery in the history of science. It will map the unseen architecture of the cosmic web, the vast filaments of dark matter, along which galaxies are strung like pearls. It will show us how stars and planets are born in our own galaxy with a clarity that will redefine astrophysics. The terror, then, is ultimately a gift. It is the feeling of standing at the edge of a vast, unknown ocean, having just discovered that your boat is far more powerful than you knew. The old maps are now useless, but the potential for discovery is limitless. It is the humility that comes from a direct confrontation with the sublime. For a century, we have been sketching a map of the cosmos. We drew the continents, named the mountain ranges, and charted the seas. We grew confident, perhaps even arrogant, in our knowledge. The James Webb Space Telescope has taken our map, a map drawn by the likes of Hubble and Einstein, and has gently, respectfully, and completely set it on fire. In its place, it is offering us a blank page and a pen filled with the light of 1 billion stars. The universe it is revealing to us is not less majestic for being strange. It is more so. It is a cosmos that is more creative, more efficient, and more mysterious than the one in our textbooks. It is a universe that does not necessarily play by the rules we have written for it, and as the golden eye continues its silent, cold vigil 1,000,000 miles from Earth, it continues to gather the ancient light, the photons that will form the next sentence, in a story that is far grander than we ever dared to believe. The terror is real, but it is the terror of awe. The fear of the unknown is being replaced by the thrill of the quest. And we, living in this unique moment in history, get to watch as the new map is drawn, one galaxy, one planet, one spectacular revelation at a time. End of script. The universe did not start quietly. Before there were galaxies, before there were stars, before time itself ticked its very first second, something extraordinary happened. The universe erupted into existence in a single, unfathomable event that we now call the Big Bang. From that instant, space began stretching, matter took form, and the seeds of everything we know were sown. Yet for all the progress, science has made, the great mystery still lingers at the very heart of it all. What caused it? What force? What spark? What unknown reality set off the chain reaction that would give rise to billions of galaxies, to planets, to life, and to us? Before we embark on this journey, tell us where in the world you're watching from. Let us know what time it is for you right now. Post it in the comments below and settle in for a fascinating journey to the beginning of time. The Big Bang Theory is the main explanation of how the universe came into being. It also explains how it has been spreading out ever since. It says that the universe began as an extremely hot, tightly packed point, and it has been growing larger with time. Scientists use the Big Bang idea to explain many important mysteries of space. They explain why certain light elements like hydrogen and helium are so common. They also explain the cosmic microwave background radiation, a faint glow of energy spread across the universe. And they explain how galaxies and other huge structures formed. One major idea linked to the Big Bang is something called cosmic inflation. This means that in the very first moments after the universe began, it spread out at an unbelievably fast rate. This quick spreading helps explain why the universe looks so smooth and even in all directions. A huge amount of scientific proof strongly supports the Big Bang Theory. And today, it is almost fully accepted by scientists. Careful calculations are based on the universe's spreading. They suggest the Big Bang happened about 13,787,000,000 years ago. This is thought to be the age of the universe. By turning back this spreading using the known laws of physics, scientists have found something. The early universe was unimaginably hot and tightly packed, but they still do not have a complete theory that can describe exactly what happened. This is true for the very first moments of the Big Bang. As the universe grew bigger, it also cooled down. This allowed tiny particles to come together and form atoms. These early atoms were mostly hydrogen with some helium and lithium. They later clumped together under the pull of gravity, helped by an unseen force called dark matter. Over time, these clumps of gas turned into the first stars and galaxies. Studies of faraway exploding stars called supernovae show that the universe is not just spreading out, it is spreading out faster and faster. This shocking finding is linked to a strange force called dark energy. Scientists still do not fully understand this force. The idea of a spreading universe was first suggested by the Russian scientist Alexander Friedmann. This happened in the year 1922. He worked out the mathematical rules now known as the Friedmann equations to explain this spreading. A few years later, in 1929, the American skywatcher Edwin Hubble gave observational proof. He proved that the universe really was spreading. He found that galaxies are moving away from Earth, and the farther away they are, the faster they seem to move. This finding is now called Hubble's law. Apart from Friedmann and Hubble, the Belgian scientist Georges Lemaître also made a suggestion. He suggested that the universe began from a single, extremely small and tightly packed point. He He named this a primeval atom. This idea, suggested in 1931, laid the base for what is now known as the Big Bang theory. The strongest piece of proof supporting the Big Bang came in 1964. It came when scientists found the cosmic microwave background radiation. This faint glow of energy was left over from the early universe. It matched the predictions made by Big Bang ideas. Its discovery convinced most scientists that another theory was wrong. This was the steady-state model, which said the universe had no beginning and had always existed. Even though the Big Bang theory explains many things, some major puzzles remain. Scientists are still trying to understand why there is more matter than antimatter. This puzzle is known as baryon asymmetry. They're also working to uncover the real nature of dark matter. This is the unseen stuff that seems to surround galaxies and hold them together. And maybe most puzzling of all, they're trying to figure out what dark energy really is, and they want to know why it is making the universe spread faster with time. The Big Bang theory depends on three main ideas. First, the laws of physics are the same everywhere. Second, the universe looks the same in all directions when looked at on a large scale. And third, the universe's matter can be thought of as a smooth, flowing substance. The idea that the laws of physics are the same everywhere comes from Einstein's theory of relativity. The second idea, called the cosmological principle, means something specific. It means if you looked at the universe from any place, it would look the same in every direction. This is true when seen on a large scale. Lastly, a perfect fluid is a way of describing matter in space. It assumes matter flows without resistance, and its pressure depends on how much matter is packed into a given space. At first, these ideas were only guesses, but scientists later tested them. For example, one way they checked the first guess was by studying the fine structure constant. This constant controls how light and matter interact. Their findings showed that this constant has barely changed. It changed by about 1 part in 100,000 over the life of the universe. The second guess, the cosmological principle, was also tested. Scientists tested it by looking at the temperature of the cosmic microwave background radiation. This radiation is the afterglow of the Big Bang. It is nearly the same in all directions, with changes of only about 1 part in 100,000. As of 1995, studies showed that on the bigger scales, the universe is mostly even. Any unevenness was at most about 1/10. The cosmological principle is very useful. It makes the rules in Einstein's theory of general relativity simpler. This leads to a mathematical model called the Friedmann-Lemaitre-Robertson-Walker metric. This model explains the shape and spreading of the universe. By assuming that matter acts like a perfect fluid, scientists work out equations. These are known as the Friedmann equations. They help predict how the universe changes with time. At the center of these equations is a single important number, the mass-energy density. This number decides both the shape of the universe and how fast it spreads. One of the biggest steps forward came when scientists figured out what the universe is made of. They did this by studying the way galaxies move and how light acts in space. They found that the matter we can see, stars, planets, and everything that shines, makes up less than 5%. The rest of the universe is something unknown. About 27% is dark matter, an unseen substance that affects gravity. However, it does not give off light. And 68% is dark energy, a strange force that seems to be pushing the universe to spread faster. Another key idea in Big Bang studies is the thought of particle horizons. Since the universe has a limited age and light moves at a fixed speed, there are limits to how far back we can see. Some light from the past simply has not had enough time to reach Earth yet. This makes what is called a past horizon, a border beyond which we cannot look. In the same way, the universe is spreading and faraway objects are moving away faster. Because of this, some of the light we send out today may never reach certain faraway parts of space. This makes a future horizon. It means there are some places in the universe that we will never be able to affect. Looking back at the very early universe, we find proof for a past horizon. But our view is also blocked by the fact that the universe was once too tightly packed. In its earlier stage, light could not move through it freely. With time as the universe spread, this horizon has moved farther and farther away. If the spreading of the universe keeps speeding up, we may also have a future horizon. This would mean some parts of the universe will one day be forever unreachable. At the very start, according to the Big Bang Theory, the universe was unimaginably hot and tightly packed. Then, with time, it began spreading and cooling down. This led to the vast universe we see today. But the moment when everything began, the exact instant of the Big Bang itself, remains a puzzle. It is a puzzle that modern physics cannot fully explain. If we turn back time using Einstein's general theory of relativity, we reach a point. At this point, the universe was so tightly packed and hot that all our known laws of physics fail. This state, known as a gravitational singularity, suggests something incredible. It suggests the universe had endless heat and endless density at some time in the past. But what that really means is unknown. General relativity alone is not enough to explain the extreme conditions of the Big Bang. Scientists believe that during these earliest moments, the effects of quantum gravity would have been the main force. This is an unknown branch of physics that joins quantum mechanics with gravity. This strange phase, called the Planck epoch, happened within a tiny fraction of a second after the universe began. It happened in the very first 100 quintillionth of a second. That is about 10 to the power of negative 43 seconds. At this moment, the universe was unimaginably small. Its size was about 1.6 times 10 to the power of negative 35 meters, and its heat was around 100 nonillion degrees, which is 10 to the power of 32 Kelvin. The conditions were so extreme that even basic particles as we know them did not exist. Scientists are still searching for a theory of quantum gravity to fully explain what happened during this time. As the universe kept spreading and cooling, the first big change happened. It occurred at 100 billionth of a trillionth of a second. This is 10 to the power of negative 37 seconds. At this time, something extraordinary happened. The universe went through a sudden and huge growth spurt, known as cosmic inflation. Within an extremely short time, it spread out exponentially. It spread much faster than the speed of light. This process smoothed out the fabric of space. It also greatly lowered the universe's heat by a factor of 100,000. It also helped explain why the universe today looks so even and balanced. Tiny quantum changes that existed during this time were stretched and made larger. These later became the seeds of galaxies and cosmic structures. Shortly after, at around 1 trillionth of a second, another important event took place. This time is 10 to the power of negative 36 seconds. One of the four basic forces of nature, the strong nuclear force, separated from the others. This left only the electromagnetic force and the weak nuclear force still joined together. This time, known as the electroweak period, set the path for more changes to come. By the time the universe was 100 billionth of a trillionth of a second, old cosmic inflation had ended. This was between 10 to the power of negative 33 and 10 to the power of negative 32 seconds. The size of the observable universe had grown by an unbelievable factor. It grew by 1, followed by 78 zeros. After this, the universe entered a stage called reheating. Here, energy from inflation was changed into matter and radiation. The temperatures became high enough to form a kind of hot, dense state. This state is known as a quark-gluon plasma. In this plasma, the basic parts of atoms, quarks and gluons, could move around freely. At this time, the universe was filled with powerful energy. Particles and their antimatter twins were constantly being created and destroyed in fast crashes. However, a strange process called baryogenesis shifted the balance in favor of matter over antimatter. For every 30 million matter-antimatter pairs, just one extra piece of matter survived. Because of this, when all the antimatter was destroyed along with matter, a very small amount of matter was left behind. This extra bit of quarks and leptons later formed everything we see in the universe today. It formed the galaxies, stars, and planets. Scientists still do not know why this uneven balance happened, but without it, our universe as we know it would not exist. These very first moments of the universe remain one of the biggest mysteries in science. While we have built strong models to explain what likely happened, much is still unknown. This is especially true for the physics that ruled the very first instant of time. Future findings in quantum physics and cosmology may one day open the secrets of the Big Bang. They may show exactly how our universe came into being. As time moved on, the universe kept expanding, which made it less dense and cooler. This cooling meant that the energy of each particle was also dropping. During this process, the basic forces of nature took on the forms we know today. One major change was the split of the electromagnetic force from the weak nuclear force. This happened in an extremely short moment, about 1/1,000,000,000th of a second after the Big Bang. Around 100 billionth of a second after the Big Bang, the universe's energy levels dropped. They dropped to a range that scientists today can study using powerful machines called particle accelerators. By the time the universe was only a millionth of a second old, tiny pieces called quarks and gluons started joining together. They formed larger particles known as baryons. These included protons and neutrons, the parts that make up atoms. Because there were slightly more quarks than their antimatter partners, this caused an uneven result. There was more matter than antimatter. When the universe cooled, even more new proton, antiproton, and neutron, antineutron pairs could no longer form. This caused almost all the leftover antimatter to be destroyed in a huge annihilation event. It left only about one matter particle for every 10 billion that first existed. A similar event took place about 1 second after the Big Bang. This was when electrons and their antimatter twins positrons also destroyed each other. At this point, the universe was mostly filled with leftover protons, neutrons, and electrons. Most of the energy was carried by light particles called photons, along with a smaller number of neutrinos. A few minutes after the Big Bang, the temperature had dropped to about 1 billion degrees Kelvin. At this point, protons and neutrons began coming together to form the first atomic centers. They mostly formed deuterium and helium. This process, called Big Bang nucleosynthesis, laid the base for the elements that would later make up stars and planets. But most of the protons did not join and stayed as simple hydrogen centers. These later became the most common element in the universe. As time went on, matter started to play a bigger role in shaping the universe. About 50,000 years after the Big Bang, the pull of gravity from matter became stronger than the effect of radiation. Then, around 380,000 years after the Big Bang, the universe had cooled enough. It cooled enough for electrons to join with atomic centers forming neutral atoms, mostly hydrogen. This stage, called recombination, was a key turning point. It allowed light to move freely through space for the first time. The remains of this ancient light can still be seen today as the cosmic microwave background radiation. After recombination, small differences in thickness across the universe caused some areas to pull in more matter. This led to the formation of huge clouds of gas. Over millions of years, these gas clouds collapsed under gravity. They formed stars, galaxies, and the large-scale cosmic shapes we see today. The type of matter in the universe plays a big part in this formation process. Scientists group matter into four main types. These are cold dark matter, warm dark matter, hot dark matter, and baryonic matter, the kind that makes up us. Based on the most exact measurements, the universe seems to follow a specific model. These measurements were taken by the Wilkinson Microwave Anisotropy Probe. In this model, cold dark matter is the main kind. Based on this model, scientists believe that dark matter makes up about 23% of the universe's total. Baryonic matter makes up only about 4.6%. The rest is thought to be dark energy, a strange force that pushes the universe to expand. Scientists have found strong proof from two different sources. These sources are exploding stars called Type Ia supernovae and the faint glow left over from the early universe. This glow is known as the cosmic microwave background. This proof shows our universe is mostly made of a strange and unseen force called dark energy. This mysterious energy is believed to spread evenly across all of space. It makes up about 73% of the total energy in the universe today. In the very early days of the universe, dark energy was likely present, but everything was packed much closer together. At that time, gravity was much stronger and acted like a brake, slowing the universe's growth. But as billions of years passed and the universe kept expanding, matter became less dense. At some point, the balance changed. Dark energy started to beat gravity, making the universe expand faster instead of slower. Scientists try to explain dark energy using Einstein's theory of general relativity. In his theory, it shows up as a math idea called the cosmological constant, but they still do not know exactly what dark energy is made of or how it works. The experts are studying its possible features through watching the universe. They are also using math and models to understand it. They're also trying to connect it to the standard model of particle physics. This model describes the basic particles and forces in nature. The way the universe has changed can be described using a science model. This model is called the lambda-cold dark matter model. This model brings together two important theories, quantum mechanics and general relativity. Quantum mechanics explains tiny particles. General relativity explains space, time, and gravity on a large scale. But what happened before the universe was 1/4,000,000th of a second old is still a great mystery. That is 1 divided by 1,000 trillion seconds. There is no simple test or theory that can fully explain that time. Understanding the very first moments of the universe is still one of the greatest unsolved puzzles in physics. The term Big Bang was first used by the British astronomer Fred Hoyle. He used it during a BBC radio talk in March of 1949. While talking about different ideas of how the universe began, Hoyle described one idea. He said that all matter in the universe was created in one Big Bang at some point in the far past. At first, people did not quickly start using this word, and it only became popular in the 1970s. Many people think that Hoyle used the phrase Big Bang as an insult. He personally supported a different idea called the steady state model. This model said that the universe has always existed and would continue forever without a beginning or end. But Hoyle later said he did not mean it in a bad way. He said he only wanted to create a strong image, an image that would make the differences between the two ideas clear. Some historians, such as Helge Krag, believe that there is little real proof that Hoyle was trying to mock the theory. Interestingly, the term Big Bang itself is somewhat misleading. It makes people think of an explosion, but the real event was not like a usual explosion that happens in one place and spreads outward. Instead, it was the whole universe itself growing from a super-hot, super-dense state. Some scientists also pointed out that the word bang makes people think of a loud sound, but sound waves cannot travel through empty space, making the name even less correct. But even though people have tried to find a better name, none have lasted. Long before the phrase Big Bang was used, scientists were already making findings. These findings pointed to the universe's growth. In 1912, an American astronomer named Vesto Slipher was the first to measure the Doppler shift in light. This light came from faraway galaxies, which were then called spiral nebulae. He found that almost all of these nebulae were moving away from Earth. At the time, people were not sure if they were separate galaxies or part of the Milky Way. Then 10 years later, in 1922, a Russian mathematician named Alexander Friedmann used Einstein's equations. He used general relativity to show that the universe might not be fixed. It could be growing or shrinking. This idea was shocking because even Einstein himself thought the universe was unchanging. Another big step came in 1924 when the American stargazer Edwin Hubble showed something important. He showed that the spiral nebulae were really other galaxies far beyond our own. He used the Hooker telescope, which was 100 inches across, to measure how far away these galaxies were. A few years later, in 1929, he made an even bigger finding. The farther away a galaxy was, the faster it was moving away from us. This link between distance and speed became known as Hubble's law. It was the first real proof that the universe was growing larger. At nearly the same time, in 1927, a Belgian scientist and priest named Georges Lemaitre reached the same idea. He also concluded that the universe was growing. He even guessed the link between distance and speed that Hubble would later confirm. But Lemaitre went even further. In 1931, he suggested that if the universe is spreading out, then at some point everything must have been packed into a single point. This point was unimaginably tiny and heavy, a primeval atom as he called it. This idea laid the base for what we now call the Big Bang theory. In the early 1920s and 30s, most scientists did not like the thought that the universe had a beginning. The main view was that the universe was endless without a starting point. Some even thought that saying the universe had a beginning sounded too much like religious stories of creation. The well-known British space scientist Arthur Eddington strongly opposed the idea. He called the idea of a beginning disgusting because it suggested that matter had not always been here. Many other scientists supported the steady-state theory. This theory said that new matter was always being made as the universe grew. This kept everything looking the same over time. During the 1930s, other possible explanations were tried. Some scientists said the universe went through cycles of spreading out and then shrinking back. Others, like Fritz Zwicky, came up with ideas such as the tired light theory. This theory said that light from faraway galaxies lost energy over time. This made it look like they were moving away. After the Second World War ended, two main competing ideas appeared. Fred Hoyle kept supporting the steady-state theory where the universe was endless and always looked the same. In his theory, new matter formed as space spread out. On the other side, scientists like George Gamow supported Lemaitre's growing universe idea and built on it. Gamow worked with Ralph Alpher and Robert Herman to form a theory. Their theory explained how elements like hydrogen and helium formed in the young universe. These same scientists also said that if the universe had once been incredibly hot and heavy, a faint glow should remain. This glow is what we now call the cosmic microwave background. Though the Big Bang theory was argued over for many years later, findings gave strong proof. This included the discovery of this cosmic background in the 1960s. This proof showed that the universe did have a beginning. Over time, what started as a disliked idea became the most widely believed explanation. It became the explanation for how the universe began. And it all started with a simple phrase, one that Fred Hoyle never meant to become famous: the Big Bang. It is quite surprising that the name Big Bang was actually made up by someone who did not believe in the idea. The name is now widely used to describe how the universe began. In March of 1949, the British stargazer Fred Hoyle used the words Big Bang. Hoyle supported a different idea, called the steady-state model. He used the phrase during a BBC radio show. He meant it in a mocking way, but the name stayed. It became the popular way to talk about the theory put forward by Georges Lemaitre. For a while, scientists were split between these two competing ideas. However, as stargazers gathered more proof, especially from radio wave studies, it became clear. The Big Bang theory was the stronger explanation. The biggest turning point came in 1964. Two scientists, Arno Penzias and Robert Wilson by chance, found the cosmic microwave background. This faint glow of energy was spread evenly across the sky. It was exactly what the Big Bang theory had predicted would be left over from the birth of the universe. With this finding, most scientists finally accepted the Big Bang. It became the best model for explaining how the universe began and grew. In the late 1960s and early 1970s, brilliant thinkers published powerful studies. Thinkers like Roger Penrose, Stephen Hawking, and George Ellis showed that based on Einstein's ideas, the universe must have started from a singularity, a point of endless heaviness and energy. Then, over the next 2 decades, space scientists worked hard to improve the Big Bang model. They also worked to solve the leftover puzzles. In 1981, the scientist Alan Guth brought forward the idea of cosmic inflation. This was a time of incredibly fast growth in the very first moments of the universe. This idea helped to explain many riddles about the shape and sameness of the cosmos. During this time, 2 main arguments kept stargazers busy. One was about the exact value of the Hubble constant, which measures how fast the universe is growing. The other was about the total amount of matter in the universe. This was thought to decide its final fate. At that time, scientists did not yet know about dark energy. This would later change our whole picture of cosmic growth. Since the late 1990s, there have been amazing steps forward in our knowledge of the universe. This is thanks to better telescope tools and space-based watches. Satellites like the Cosmic Background Explorer, the Hubble Space Telescope, and the Wilkinson Microwave Anisotropy Probe have given exact readings of the key parts of the universe. Perhaps the most surprising finding came when scientists learned about the universe's growth. It is not slowing down as was once thought. Instead, it is actually speeding up. This effect is now blamed on the strange force called dark energy. Today, the Big Bang theory is still the best explanation for how our universe came to be, and researchers keep on uncovering new and thrilling details about its beginning and its fate. The Big Bang theory gives a clear explanation for many of the wonderful things we see in the universe. It helps us understand why certain light elements like hydrogen and helium exist in certain amounts. It also explains why we can still see a faint glow called the cosmic microwave background. It explains how galaxies are arranged in huge groups, and it explains why they seem to be moving away from us, as is shown by Hubble's law. These key pieces of proof are often called the 4 pillars of the Big Bang model. They strongly support the idea that the universe started from a single point, and that it has been spreading out ever since. One of the first signs that the Big Bang theory was right came from a finding: galaxies are moving away from us. We can tell by looking at how their light is stretched into longer, redder waves. This is a happening called a redshift. Another major step was the discovery of the cosmic microwave background. This is a faint signal left over from the young universe. Scientists also prove that the amounts of light elements in space match their guesses. These guesses come from a process called Big Bang nucleosynthesis. This explains how these elements were formed in the universe's first moments. In recent years, stargazers have gathered even more proof. They have done this by studying how galaxies form and how huge cosmic structures are spread across space. To fully explain the Big Bang, scientists have put forward some strange ideas. These include dark matter and dark energy. Dark matter is believed to make up most of the universe's weight, yet we cannot see it directly. We only notice its pull on galaxies and gravity. Many tests are going on to find out what dark matter really is. Dark energy, on the other hand, is thought to be the cause of the universe's fast growth, but what it truly is remains unknown. There are also other puzzling questions. For example, why small galaxies act differently than expected, and why the centers of galaxies seem to have more dark matter than our models suggest. When we look at faraway galaxies and quasars, we see that their light has shifted toward the red end of the spectrum. This red shift happens because the universe itself is spreading out. It is stretching the light waves as they travel through space. If we measure how much the light has shifted and compare it to how far away these objects are, we find a clear pattern. This pattern is known as Hubble's law. This law tells us that galaxies that are farther away from us are moving away faster. They move faster than those that are closer. The idea that the universe is spreading out was first guessed in the early 1920s. It was guessed by scientists like Alexander Friedman and Georges Lemaitre. It was not until 1929 that Edwin Hubble gave real proof through watching the skies. This changed our understanding of the universe forever. One way of measuring the expansion is based on studying the cosmic microwave background. This method gives a lower number. Another way is based on measuring the distances to galaxies, which gives a higher number. Scientists are still trying to figure out why these two numbers do not match. One of the biggest finds that confirmed the Big Bang theory happened by accident in 1964. Two scientists, Arno Penzias and Robert Wilson, were working with a radio antenna. They came across a strange background noise that seemed to come from every direction in space. This turned out to be the cosmic microwave background. It was leftover heat from the universe's earliest moments. Their find matched the guesses that were made by other scientists in the 1950s. This gave stronger support to the Big Bang theory. Because of this, Penzias and Wilson won the Nobel Prize in Physics in 1978. The cosmic microwave background is a faint glow left over from a time when the universe was extremely hot and dense. At that time, space was filled with a thick fog of charged particles. This made it impossible for light to move freely. About 372,000 years after the Big Bang, these particles joined together. They formed neutral atoms which made the universe clear for the first time. The light from that moment is what we now see as the cosmic microwave background. In 1989, NASA sent a satellite called COBE into space. COBE was short for the Cosmic Background Explorer. It made two major finds. First, in 1990, it proved that the cosmic microwave background had a perfect blackbody spectrum. This was just as expected. Then, in 1992, it found tiny temperature changes across the sky. These small differences later grew into galaxies and stars. These finds were so important that John C. Mather and George Smoot won the Nobel Prize in Physics in 2006. In the years that followed, experiments on the ground and on balloons gave even more exact measurements. These were measurements of the cosmic microwave background. In the year 2000, an experiment called Boomerang measured the pattern of these small changes. It showed that the universe is almost flat in shape. Then, in 2003, data from the Wilkinson Microwave Anisotropy probe gave the most exact numbers yet. It provided numbers for key cosmic details, which helped improve our knowledge of the early universe. In May of 2009, the European Space Agency sent up the Planck space probe. It gave even clearer measurements of the cosmic microwave background. Many other experiments, both on Earth and in space, still study this faint glow. They give us a deeper knowledge about the beginning and growth of the universe. Although the Big Bang theory explains a lot, many mysteries remain. Scientists are still trying to understand dark matter, dark energy, and the exact details of what happened in the first moments. With new tools and ongoing study, we may one day uncover the full story. We may learn how our universe began and what its final fate might be. Scientists have used Big Bang models to guess how much of certain light elements exist in the universe. These elements are helium, deuterium, and lithium compared to normal hydrogen. More exactly, they can predict the amounts of helium-4, helium-3, deuterium, and lithium-7. These amounts depend on one key factor, the number of photons compared to the baryons. This photon-to-baryon ratio can also be worked out. It can be found by studying the tiny temperature changes in the cosmic microwave background. This is the faint glow left over from the young universe. According to these numbers, helium-4 should make up about 1/4 of the universe's total hydrogen mass. Deuterium should be about 1/1000th of that mass, helium-3 should be about 1/10,000th, and lithium-7 should be an extremely tiny part, about 1/10 billionth of hydrogen's mass. When astronomers measure the real amounts of these elements in space, they mostly agree. The amounts agree with what the Big Bang theory predicts. The agreement is especially strong for deuterium. Helium-4 is slightly off from the predictions, but still close. Lithium-7 is different by a factor of 2. This is a puzzle known as the cosmological lithium problem. Some of this difference may come from the limits in how well we can measure. Even with these small gaps, the overall match between the predictions and what we see is strong proof. It is proof that the Big Bang really happened. This theory is still the only clear reason why the light elements exist in the amounts that they do. In fact, it would have been almost impossible for the Big Bang to have made much more or much less than 20 to 30% helium. Without the Big Bang, there is no clear reason why the early universe should have had more helium than deuterium. This was long before the stars were formed. There is also no clear reason why these elements should be found in fixed amounts across the universe. Scientists have closely studied the shapes and the spread of galaxies and quasars. Their results match what the Big Bang theory predicts. By joining real observations with scientific models, they have learned something important. The first galaxies and quasars started to form within about 1 billion years after the Big Bang. Over time, these cosmic structures have grown into huge clusters of galaxies. They have also grown into even bigger superclusters. As the universe has aged, the stars inside the galaxies have changed. When astronomers look at galaxies that are very far away, they are really seeing them as they were billions of years ago. They are seeing them in the early universe. These faraway galaxies look quite different from the ones closer to us. The closer ones show a more recent stage of cosmic change. The galaxies formed more recently do not look the same as galaxies formed at similar distances soon after the Big Bang. This clearly goes against the old steady-state theory. That theory claimed that the universe was always the same and had no beginning. Scientists have also found that the patterns of star birth, the spread of galaxies, and the structure of the universe all match very well. They match what Big Bang computer models predict. These finds are helping scientists to better understand how the universe took shape. In 2011, astronomers made a stunning find. By studying the light from faraway quasars, they saw what seemed to be untouched clouds. These were clouds of the very first gases in the universe. Before this, every object ever seen in space contained heavy elements. Elements like carbon, oxygen, and silicon were made inside stars. But these two gas clouds had no signs of such elements. This means that they likely were formed just minutes after the Big Bang. They formed during an event called Big Bang nucleosynthesis. Scientists have also worked out the age of the universe by using different methods. One method measures the rate of the universe's growth with the Hubble constant and the cosmic microwave background. Another method guesses the ages of the oldest stars. It does so by studying their life cycles in globular clusters and measuring radioactive elements inside them. More proof comes from studying faraway supernovae and the small temperature changes in the cosmic microwave background. All of these different tests point to the same age. This strongly supports the main cosmological model known as the lambda-cold dark matter, or LCDM model. Still, some of the results raise questions. One very puzzling object is a quasar called APM 08279 plus 5255. It seems to have a lot of water. This suggests that the universe was making a lot of water at a much earlier time than was expected. Some scientists say that this does not fit with the main Big Bang idea. Others argue that it may have been caused by other factors like gravitational lensing. In a similar way, some galaxies recently found by the James Webb Space Telescope seem too well formed. They seem too formed to exist so early in the universe. This is challenging our ideas of how quickly large structures can form in the LCDM model. Another major Big Bang guess is that the cosmic microwave background's temperature was hotter in the past. The studies of faraway gas clouds support this. They show small absorption patterns in their light. This also suggests that a certain cosmic effect, the Sunyaev-Zeldovich effect, should stay mostly the same. It should stay the same no matter how far away a galaxy cluster is. Scientists have seen this to be roughly true, though it is hard to measure. This is because galaxy clusters themselves change over time. In the future, new gravitational wave observatories may be able to spot ancient gravitational waves. These are ripples in space-time that could let us see the universe less than 1 second after the Big Bang. If that happens, it could be one of the greatest leaps forward in knowing how our universe began. The Big Bang theory has helped scientists learn how the universe started, but it has also brought many new puzzles. Some of these mysteries have been solved, but others remain. In fact, every time that scientists solve one problem, new questions often appear. For example, the horizon problem, the magnetic monopole problem, and the flatness problem are usually explained. They are explained by the idea of cosmic inflation, but many of the details about this inflation period are still unclear. And some scientists, even those who first came up with the idea now, think that it may not be right. One of the biggest unanswered questions is why there is more matter than antimatter in the universe. According to today's theories, when the universe was extremely young and very hot, it should have had equal amounts of matter and antimatter. But if that were true, matter and antimatter would have destroyed each other, leaving nothing. Instead, the universe that we see today is almost fully made of normal matter. To explain this, scientists came up with a process called baryogenesis. For this to work, 3 specific conditions called the Sakharov conditions must be met. These are the number of baryons, particles like protons and neutrons, must not always stay the same. Certain basic symmetries called C-symmetry and CP-symmetry must be broken, and the universe must have moved away from a thermal balance at some point. While these things can happen in the standard model of physics, they are not strong enough. They cannot fully explain why there is so much more matter than antimatter. Scientists are still looking for a full answer. Findings from exploding stars called Type Ia supernovae have shown that the universe's growth is not slowing down. It is actually speeding up. This was shocking, since scientists once thought that gravity would slow it down over time. To explain this, they came up with the idea of a strange force or energy called dark energy. Dark energy is thought to make up most of the universe's energy. Scientists studying the faint glow from the Big Bang, the cosmic microwave background, have found something. The universe is almost perfectly flat in shape. According to Einstein's theory of general relativity, this means something. The total mass and energy of the universe must be very close to a value called the critical density. But when scientists measure the real amount of matter, they find that it makes up only about 30% of the critical density. This means that the other 70% must come from something else, dark energy. Dark energy also helps to explain the overall shape of the universe. It does this by affecting huge cosmic structures. It changes how often gravitational lensing happens when light from faraway objects bends around huge galaxies. It also changes how sound waves move through the young universe. This leaves marks called baryon acoustic oscillations. Even though dark energy is the best guess for these effects, its true nature is still unknown. Some scientists think that it may be tied to a vacuum energy. Others think of more unusual ideas. Data from the Wilkinson Microwave Anisotropy Probe in 2008 showed something important. The universe is made of about 73% dark energy and 23% dark matter, and 4.6% normal matter and less than 1% neutrinos. Interestingly, as the universe grows, the share of matter goes down, while dark energy stays nearly the same. This means that dark energy will keep on playing a bigger and bigger role in the far future. Another big mystery is the existence of dark matter. This is a kind of matter that cannot be seen directly, but it has a strong pull of gravity on galaxies. In the 1970s and 80s, astronomers found that there was not enough visible matter, not enough to explain the gravitational forces that were keeping galaxies together. This led to the idea that most of the universe's matter must be invisible. Some guesses suggest that up to 90% of all matter in the universe is dark matter. Without dark matter, many of the things we observe do not make sense. For example, galaxies spin much faster than expected. This means there must be an extra unseen mass keeping them together. The large shape of the universe would not have formed in the way that we see it today. The amount of an element called deuterium in the universe is far lower than expected if dark matter did not exist. Even though scientists have never directly found dark matter particles, its presence is understood. It is understood through different observations. These include the way that galaxies move inside clusters and the bending of light due to gravitational lensing. They also include the spread of hot gas in galaxy clusters and the small changes in temperature in the cosmic microwave background. Physicists have suggested many possible types of dark matter. This includes unusual particles that do not interact with normal matter except through gravity. Experiments in many places around the world are trying to detect these particles, but none of them have been found yet. Even though it is the best explanation for many cosmic observations, the dark matter idea is not perfect. There are some problems that are still not explained. This includes the dwarf galaxy problem. Computer models predict that there should be far more small galaxies than we actually see. And there is the cuspy halo problem. The centers of galaxies should have a sharp rise in dark matter density, but observations show a smoother spread. Some scientists have suggested other ideas that change our understanding of gravity instead of needing dark matter. However, none of these other ideas have been able to explain all of the observations. They have not explained them as well as the dark matter model. One of the biggest challenges in modern physics is the cosmological constant problem. This is sometimes called the most embarrassing problem in physics. This comes from the fact that the amount of dark energy in the universe is very different. It is different from the value predicted by quantum physics. According to calculations based on basic physics, the energy density of empty space should be much larger. It should be much larger than what is actually seen. Scientists do not have a clear explanation for why the universe's dark energy is so small compared to these predictions. To solve this, some researchers think that dark energy could be linked to Einstein's cosmological constant. This was a term that he first added and later dropped in his equations. Others suggest more complex ideas such as quintessence. This idea says that dark energy changes over time instead of staying the same. Even with all the progress scientists have made in understanding the universe, many mysteries remain. The nature of dark matter and dark energy is still unknown. The imbalance between matter and antimatter and the strange speeding up of the universe's growth are all puzzles. Astrophysicists are still working on them. Each new discovery brings us closer to the answers, but it also often opens the way to deeper mysteries. The search to uncover the secrets of the cosmos continues, and the answers may change our understanding of the universe in ways that we cannot yet guess. The horizon problem comes from a simple but mind-twisting idea. Nothing, not even information, can move faster than light. Since the universe has only existed for a limited amount of time, this means something. Only certain parts of space could ever have touched or influenced each other. The line that marks how far any influence could have reached is called the particle horizon. Here is where the problem appears. When we look at the cosmic microwave background, the faint glow from the early universe, it looks almost the same in every direction. But if the universe had always been filled only with radiation and matter, this would not be so. Regions that were more than about 2 degrees apart in the sky should never have had the chance to share heat or energy. So how did they all end up at the same temperature? The answer to this puzzle comes from a powerful idea called inflation theory. This theory says that at an extremely early time, the universe was filled with a strange even energy field. This was long before atoms or even basic particles like protons and neutrons existed. During this time, the universe expanded at an incredibly fast rate, growing unimaginably quickly. Because of this sudden expansion, areas that today seem impossibly far apart were actually close together. They were close before inflation started. That means they could have shared heat and balanced their temperatures before being pushed apart by inflation. This explains why the cosmic microwave background looks so smooth and even across the sky. There is another amazing effect of inflation: quantum fluctuations, the tiny random energy blips predicted by Heisenberg's uncertainty principle, were stretched to enormous sizes. These small changes became the seeds of the galaxies, stars, and cosmic structures that we see today. Inflation predicts that these early changes were almost perfectly balanced, and modern studies of the cosmic microwave background confirm this. While inflation explains a lot, it raises another hard question. According to most models, inflation ended long before the electroweak era. This was the time when basic forces like electromagnetism and the weak nuclear force split. If the faraway parts of the universe were already cut off from each other by then why don't we see big uneven patterns? Why don't we see them in the universe today? This is still an open question in cosmology. Back in the 1970s, physicists working on grand unified theories predicted something. They predicted the existence of magnetic monopoles, particles that act like single north or south poles of a magnet. These objects should have been formed in huge numbers in the early high-energy universe. But after many decades of searching, no one has found even one of them. Inflation solves this puzzle in a simple way. It stretched the universe so much that any monopoles that did exist were spread out. They were spread so widely that they became almost impossible to detect. Another strange feature of the universe is its flatness. Space can be positively curved like a sphere, negatively curved like a saddle, or flat like a sheet of paper. The shape depends on the universe's total energy density. If the density had been even slightly different in the past, the universe would have either collapsed long ago or expanded into a nearly empty void. Yet, after billions of years, it still looks amazingly flat. To make this clear, at the time of nucleosynthesis, the density of the universe had to be extremely precise. This was when the first atomic nuclei were formed just a few minutes after the Big Bang. The density had to be within 1 part in 10 quadrillion of the perfect value. This was needed to stop either a runaway collapse or an endless growth. That level of balance is very hard to explain unless something actively pushed the universe toward flatness. Inflation gives the answer again. Just as a balloon that is being blown up smooths out its surface, the extreme stretching of space during inflation forced the universe toward flatness. This makes sure that we live in a cosmos that still looks balanced today. Many people wrongly believe that the Big Bang Theory explains how everything first came into being. This includes time, space, and energy, but that is not quite true. The Big Bang Theory does not tell us what caused the universe to exist. It explains how the universe that we see today grew from an extremely small, very hot and dense state. A common mistake is thinking of the Big Bang as a small object suddenly expanding like a balloon. But when scientists talk about the size of the universe at the time of the Big Bang, they mean only the part we can observe. The entire universe may be far larger, or maybe even infinite, and we may never fully know its true size. Another mistake is thinking of the Big Bang as an explosion where matter was thrown apart. It was not like the pieces from a bomb. In reality, what happened was the stretching of space itself. It was like a growing fabric that was carrying the galaxies with it. Some scientists call this the stretching of space, while others call it objects moving apart. Both views can be correct depending on how you look at it. According to Hubble's law, the farther away a galaxy is, the faster it seems to move away. Some galaxies even seem to be moving faster than light, but this does not mean that they are breaking the laws of physics. Instead, space itself is stretching. This is making the distances between galaxies grow faster with time. This is not the same as objects moving inside a space. Many people have heard that the redshift of faraway galaxies is caused by the stretching of space. While this is partly true, the most straightforward explanation is the Doppler effect. This is the same effect that makes a passing ambulance sound different as it moves toward or away from you. In this case, as light travels across the universe, it gets stretched into longer wavelengths. It shifts toward the red part of the spectrum. Scientists can make guesses about what will happen to the universe, but they can only do this for a limited stretch of time, although that limit is far longer than the present age of the universe. Beyond that point, things become much less clear. In the same way, while scientists have learned a lot about the universe's first moments, the real beginning of everything is still not known. When the Big Bang first took place, the universe was unimaginably hot and dense. The Belgian scientist Georges Lemaitre called this starting point the primeval atom. Another scientist, George Gamow, used the word to describe the thick material that filled the early universe. We still do not know exactly how or why this first state appeared, but the Big Bang idea does give us some hints about how the universe changed afterward. Scientists have also suggested that our universe is steady because of the way that natural laws work. Some ideas even suggest that there could be an endless number of universes, and only those with the right conditions could create life. But what was there before the Big Bang? This is one of the greatest puzzles in physics. The Big Bang idea is built on Einstein's general relativity, but at an extremely high heat, this idea no longer works. To truly understand the very first moments of the universe, scientists need a new idea. They need an idea that joins gravity and quantum mechanics, something called quantum gravity. Some theories even suggest that time itself may not have existed before the Big Bang. This means that asking what happened before might not even make sense. Although we do not yet have clear answers, scientists have come up with many interesting ideas. These ideas are about what might have happened before or during the Big Bang. The quantum fluctuation model. This idea says that the Big Bang may have been caused by a sudden random change in a quantum field. Even though it seems extremely unlikely, in an endless amount of time, even the rarest events can finally take place. The emergent universe. Some ideas describe the universe as existing forever in a low-energy state. Then it suddenly moves into an expanding state, much like old myths about the universe being born from a cosmic egg. The no-boundary model, which was suggested by Stephen Hawking and James Hartle, this idea says that the universe did not have a beginning in the normal sense. Instead of one single point, time and space smoothly appeared from a limited past. Brain cosmology, which is based on string theory. This idea says that our universe sits on a giant brain, a higher dimensional surface. The Big Bang may have been caused by a crash with another brain, a cyclic universe. This idea says that the universe does not have a true beginning or an end. Instead, it grows and shrinks in an endless loop. The Big Bang could have been the result of a past universe that was falling in on itself. Eternal inflation and the multiverse. According to this idea, different parts of the universe may grow at different speeds, forming bubble universes. Our universe could be only one bubble among countless others in a much bigger multiverse. Even though scientists have learned an amazing amount about the Big Bang, many questions are still not answered. Future findings in quantum physics, gravity, and the study of the universe may one day explain what happened. They may explain what happened in those first unimaginable moments or even before. Until then, the story of the universe remains one of the greatest puzzles of all time. Before scientists discovered dark energy, they had two main ideas about how the universe might end. The first idea was that if the universe had too much weight, its pull would finally slow its growth. Then, it would bring everything back together. Over billions of years, the universe would stop growing, shrink, and get hotter and denser. It would do this until it fell into an incredibly small and fiery state, just like it was at the very start. This idea is called the Big Crunch. The second idea was that if the universe had just the right amount of weight, or even less, it would keep on growing forever. But it would grow more and more slowly. Over time, the stars would use up all of the gas in the galaxies. This means that no new stars could be born. The stars that remained would at last burn out. They would leave only cold, dead leftovers like white dwarfs, neutron stars, and black holes. These leftovers would crash together and join, making bigger black holes. At the same time, the universe would keep on cooling. Its heat would slowly move toward absolute zero, a state called the Big Freeze. If protons, the basic parts of atoms, are not steady, then all of normal matter would at last break down. This would leave only radiation and black holes. Over unimaginable stretches of time, even black holes would fade away. They would fade as they slowly release energy through Hawking radiation. At this point, the universe would have reached a heat death. This means that all useful energy would be gone and nothing could happen anymore. But newer discoveries show that the universe is not just growing. It is actually growing faster and faster because of a strange force called dark energy. This means that more and more galaxies will finally move so far away from us. They will move so far that we will never be able to see or reach them again. Scientists still do not know exactly how this will end, but one widely accepted idea is called the lambda-cold dark matter model. It says that galaxies and other groups held together by gravity will stay whole. Meanwhile, everything else grows colder and lonelier, leading to a heat death. There is another more dramatic idea known as the Big Rip. If dark energy grows stronger with time, it could one day tear apart everything. It would tear apart not just galaxies and stars, but even planets, atoms, and the smallest parts of matter. In this case, the universe would not just fade into stillness. It would be torn apart fully. Beyond science, the Big Bang, the event that began the universe, has stirred deep talks in religion and philosophy. Some people see it as proof of a divine creator. Others think that it removes the need for one. This debate has made the Big Bang one of the most interesting meeting points between science and belief. As we try to understand where our universe came from, we run into one of the biggest puzzles in modern science. This is the singularity. This strange point lies at the very center of the Big Bang, and scientists believe that everything we see today, space, time, matter, and energy, came from it. But this leads to an even bigger question. What existed before the Big Bang? Imagine a place where the rules of physics stop making sense. A singularity is a point where matter is squeezed into an endlessly tiny space. It becomes so dense that gravity becomes unbelievably strong. In this extreme state, space and time twist and collapse in ways that we cannot fully understand. Even the most advanced scientific equations like Einstein's general theory of relativity fail to describe what happens. They cannot describe what happens inside a singularity. This means that based on what we know now, the laws of physics simply stop working. The singularity that started our universe was even more unbelievable than the ones found in black holes. Instead of being trapped inside a collapsing star, this singularity marked the very beginning of everything. At that moment, all of existence was squeezed into a tiny, unimaginably hot and dense point. This was a state where no known physical laws applied. Then, in a single instant, this singularity expanded with incredible power. It gave birth to space, time, and all of the matter that would later form galaxies, stars, and planets. This explosive event is what we now call the Big Bang. Asking what happened before the Big Bang is difficult. It is difficult because it assumes that time already existed. But according to Einstein's theory of relativity, space and time are woven together. They form one fabric called spacetime. If the Big Bang created space-time itself, then time as we know it did not exist before that moment. In other words, the very idea of a before might not even make sense. However, some scientists believe that there might be more to the story. Several ideas try to explain what could have come before the Big Bang. Some scientists suggest that the universe did not come from nothing. Instead, it goes through endless cycles of birth, expansion, and collapse. In this model, the universe expands for billions of years, reaches a peak, and then shrinks back. It shrinks into a singularity before exploding into another Big Bang. If this idea is correct, then something has always existed. Our current universe is just the newest version in a never-ending chain of universes. Quantum physics, the strange science that describes tiny particles, suggests something else. It suggests that tiny bits of matter and energy can appear and disappear, even in what seems to be empty space. Some scientists think that the entire universe may have come from one of these random quantum changes. In this view, before the Big Bang, there was a vast emptiness. In this emptiness, tiny, unpredictable quantum events took place. At some point, one of these events led to the birth of our universe. Another idea suggests that our universe is just one of many. According to the multiverse theory, an endless number of universes exist, each with its own unique rules. If this is true, then our universe was not the first and will not be the last. Something has always existed. It just was not necessarily our universe. Before the Big Bang, there may have been another universe, or an entirely different state of reality. In the 1970s, the brilliant physicists Stephen Hawking and Roger Penrose made groundbreaking discoveries. They made discoveries about singularities. By joining Einstein's general relativity with quantum mechanics, they gained new knowledge. Quantum mechanics are the strange rules that control tiny particles. Their study showed that singularities are not just ideas on paper, they are real points where physics as we know it collapses. They proved that if you rewind time to the very start of the universe, you reach a moment. At this moment, space bends endlessly, and time itself stops working in any normal way. This means that before the Big Bang, there was no familiar space, no ticking clock, and no past. There was just an impossible state of endless density. Science has given us amazing knowledge about how the universe grew after the Big Bang. But the moment before remains one of the greatest mysteries. If time itself began with the Big Bang, then asking what came before might not make sense at all. However, many scientists believe that we simply have not yet found the right laws of physics, not the laws needed to explain what happened. In our daily lives, time feels like an unstoppable river. It is always moving from one moment to the next. We naturally think in terms of before and after, a yesterday, a last year, and even thousands of years ago. But when we try to use this logic to explain the birth of the universe, things become far more complicated. At the heart of this great mystery is the idea of the singularity. This is a point where all known rules of physics stop making sense. Some scientists think that time itself began with the Big Bang. This means that there was no before at all. In this view, asking what happened before the Big Bang would be like asking what lies beyond the North Pole. There is simply no direction left to go. This suggests that time as we know it only exists inside our universe, and it did not exist before it was born. But not all scientists agree with this view. Some of them believe that the singularity may not have been the true beginning. Instead, it came from something that already existed. One idea suggests that the universe could have come from tiny random bursts of energy in an empty void. These unpredictable changes somehow sparked the birth of everything. Another idea suggests that our universe is just one in a never-ending cycle. In this cycle, an older universe collapsed in on itself and then gave birth to a new one. While these ideas are very uncertain and stretch the limits of human understanding, they open the door to exciting possibilities about what might exist beyond what we can see. One of the greatest minds to explore these mysteries was the famous physicist Stephen Hawking. He spent much of his life studying black holes. These are strange objects in space where gravity is so strong that nothing can escape. Not even light can escape. Interestingly, the center of a black hole has a singularity. It is much like the one thought to exist at the beginning of the universe. By studying black holes, scientists hope to uncover secrets about the first moments of existence. In one of his most groundbreaking discoveries, Hawking revealed something. He revealed that black holes are not completely dark as people once thought. Instead, they slowly release energy in the form of what is now called Hawking radiation. This discovery was surprising because it meant that black holes can shrink over time and eventually vanish. It also raised an even deeper question. When a black hole fades away, what happens to all the information that it once contained? Does it truly disappear, or could there be some hidden way for it to survive? This puzzle challenges our very understanding of the universe. The study of singularities reveals a major problem in modern science. This is true whether they are inside black holes or at the birth of the universe. The two most powerful theories we have, Einstein's general theory of relativity and quantum mechanics, do not work together. General relativity explains gravity and the movement of large objects like planets and galaxies. Quantum mechanics describes the tiny world of atoms and particles. At the extreme conditions of a singularity, these two great theories fall apart. This leaves scientists searching for a better explanation. Many physicists believe that the missing key is something called quantum gravity. This is a theory that would combine relativity and quantum mechanics into one complete framework. If such a theory were found, it could help us understand what really happens inside a black hole. It could help us understand what took place during the Big Bang and whether anything existed before it. For many decades, scientists have worked tirelessly to uncover this missing link. They have created countless ideas and built complex mathematical models, but so far, no one has been able to fully prove how gravity works on the smallest quantum level. This puzzle is crucial because it prevents us from fully understanding one of the most important events. This event is the singularity at the birth of everything. The singularity is not just the starting point of our universe, it also represents a barrier to our knowledge. It marks the moment when space, time, and matter first appeared. Yet it also stands as a wall that science has not yet broken through. In our everyday lives, we understand reality in simple ways. Things have causes and effects, space has 3 dimensions, and time moves forward like an arrow. But the singularity questions all of these ideas. It forces us to think beyond what we can see, measure, or even fully imagine. What if the laws of physics that we rely on only began to exist after the Big Bang? What if time itself as we know it was not present before that moment? These questions lead us to some of the oldest and deepest puzzles ever considered by humanity. What does it mean to exist? How did something come from nothing? Can we ever truly understand the exact moment when the universe was born? These thoughts have fascinated philosophers, scientists, and thinkers for thousands of years, and they remain at the center of our search for knowledge. As technology improves, we continue pushing the limits of what we know. Powerful telescopes allow us to look deeper into space. Particle colliders help us study the tiniest building blocks of reality, and new ideas try to connect the vast and the tiny into one complete picture. Yet the singularity remains a mystery, an unsolved puzzle that challenges us to stretch our minds. It challenges us to go beyond everything that we currently understand. It is both an invitation and a challenge, calling us to explore the greatest secrets of the universe and to explore the true nature of reality itself. When we think about the beginnings of the universe, we often picture an empty space before anything existed. But modern science tells a very different story, one that questions our deepest understanding of reality. Instead of a cold, lifeless emptiness, what we once thought of as empty space is actually an unseen, buzzing place. It is filled with energy and strange activity. This leads us into the fascinating world of quantum physics. This is a part of science that studies how the universe works at the very smallest levels. At the heart of quantum physics is a surprising discovery. Space, even when it is stripped of all matter and light, is never truly empty. Instead, it is alive with what scientists call quantum fluctuations. These are tiny, unpredictable flashes of energy that appear and disappear in an instant. These fluctuations are not just random events. They are the base of some of the most amazing discoveries in modern science. They might even hold the answer to one of the greatest mysteries of all. How did the universe begin? For thousands of years, people believed that if you took away everything from space, you would be left with a true emptiness. This includes every atom, every particle, and every bit of light. This idea of nothingness was widely accepted by scientists and thinkers alike, but discoveries in quantum physics in the past 100 years have completely overturned this belief. In truth, what looks like an empty space is far from empty. Instead, it is a restless sea of energy, always moving and changing because of quantum fluctuations. These fluctuations happen because of something called the uncertainty principle. This is a key idea in quantum physics that was introduced by the scientist Werner Heisenberg. This principle says that at the most basic level, we can never know both the exact position and the exact speed of a particle at the same time. This unavoidable uncertainty leads to a strange outcome. Even in what we see as a vacuum, energy constantly flickers in and out of existence. This restless and unpredictable activity creates what scientists call a quantum foam. This is an unseen, churning sea of energy at the tiniest levels of reality. Even though we cannot see it with our eyes, its effects can be measured and have been proven through experiments. The first strong evidence that empty space contains energy came in 1947. It came thanks to two Dutch scientists, Hendrik Casimir and Dirk Polder. They carried out a simple but groundbreaking experiment that revealed one of the strangest forces in the universe. This is now called the Casimir effect. In their experiment, Casimir and Polder placed two small flat metal plates very close together inside a vacuum. This was a place where, according to classical physics, there should be nothing at all. If space were truly empty, then nothing should have happened. But to their amazement, the plates moved toward each other as if an unseen force was pulling them together. At first, this seemed impossible. What could be causing this strange pull between the plates? The answer lay in the quantum fluctuations of space itself. Even in a vacuum, energy fluctuations occur all around the plates. However, because the plates were placed so close together, they blocked certain kinds of fluctuations from happening between them. Meanwhile, the space outside the plates still had all of the possible quantum fluctuations happening freely. This imbalance in quantum energy created a pressure pushing the plates together. This discovery was revolutionary. It showed that what we thought was nothing was actually full of unseen energy. The Casimir effect gave direct experimental proof that quantum fluctuations were real, and it proved that even a vacuum is never truly empty. Now this is where things become even more amazing. If the empty space of the universe is filled with these tiny bursts of energy, could they have played a role in the birth of the universe? Many scientists believe that the answer is yes. According to some of the most widely accepted ideas in modern cosmology, the entire universe may have been born from a quantum fluctuation. It may have been born in a very early vacuum. Think of it like this: instead of the universe emerging from an absolute nothingness, it might have come from a state where energy was already present. This energy was hidden beneath the surface, waiting for the right moment. Under the right conditions, one of these quantum fluctuations could have suddenly expanded. This would cause what we now call the Big Bang. This idea is supported by quantum field theory and the theory of cosmic inflation. This theory suggests that the universe went through an unbelievably fast expansion in its earliest moments. Instead of a universe coming from a complete nothingness, it may have burst forth from a quantum vacuum. This was a place where energy and fluctuations were already bubbling beneath the surface. Even after the Big Bang, quantum fluctuations continued to shape the universe. Right after the universe began, it was unimaginably hot and full of energy. During this time, quantum fluctuations acted like tiny seeds in the fabric of space. At first, these fluctuations were incredibly small, almost impossible to notice. But as the universe expanded, these tiny differences in energy spread out over huge distances. Over billions of years, these tiny variations in energy and density grew under the pull of gravity. Slowly but surely, these fluctuations became the base for galaxies, stars, and planets. Without them, the universe might have stayed perfectly smooth and empty, and life as we know it might never have appeared. The idea of cosmic inflation, which was first suggested by the scientist Alan Guth, explains something. It explains how these quantum fluctuations were stretched to huge scales in the early universe. This rapid expansion magnified the tiny variations in energy. It turned them into the large-scale structures that we see in the universe today. The thought that quantum fluctuations could give rise to a whole universe is both exciting and unsettling. If our universe came from a quantum fluctuation, then could it be only one of many? Some scientists believe that our universe is just one of countless others that may have been formed in the same way. This leads to the idea of the multiverse. The multiverse suggests that quantum fluctuations might be constantly creating new universes. Each would have its own unique rules and laws of physics. In this view, what we see as reality might just be a small part of a much larger cosmic landscape. Universes might be popping into existence and disappearing all the time. The discovery of quantum fluctuations has broken the old idea of nothingness. It shows that even in the most barren parts of space, there is a hidden, restless energy at work. This is an energy that may have given birth to the universe itself. Even more surprising is the idea that the universe may not need a traditional cause to exist. In our daily lives, everything happens for a reason. Every effect must have a cause. But in the strange and unpredictable world of quantum physics, things can happen on their own. They can happen without any clear reason. Particles can pop in and out of existence, and energy can appear and vanish in an instant. And under the right conditions, a single quantum fluctuation might have created the universe as we know it. this shakes everything that we think we know about reality. If the universe could arise from quantum fluctuations, then does that mean that reality itself is built on randomness? The idea that our entire universe might have started from an almost invisible ripple in the fabric of quantum energy is both astonishing and mind-expanding. It forces us to face one of the deepest mysteries of all time. How did the universe create itself? Quantum physics, the part of science that studies the tiniest building blocks of reality, gives us a surprising answer. It suggests that what we think of as nothing is not truly empty. Instead, it is an unseen, ever-changing space filled with hidden energy. It is always shifting in ways that we cannot see. Imagine a cosmic stage where invisible forces are always at work. Tiny bursts of energy are flickering in and out of existence like sparks. These short-lived fluctuations may seem small, but under the right conditions they could act as the first sparks. They could light the birth of something far greater, maybe even an entire universe. Scientists have long explored this mind-stretching idea through quantum field theory. This is a system that tries to explain how these mysterious energy shifts work. But this field of study is still young, and many questions remain unanswered. How exactly could these quantum fluctuations have led to the vast and structured universe we see today? What forces guided the change from chaos to order? The truth is that we are only beginning to uncover these cosmic secrets. Yet the thought that our universe could have come from an unseen quantum-driven event changes our whole view of creation. It gives us a bold and unconventional way of looking at things. In this view, the universe may have been born not from an outside force or a divine command, but it may have been born from the strange and powerful properties of space itself. While much is still unknown, one thing is certain. The more we explore, the more we realize that reality is far stranger, more complex, and more incredible than we ever dreamed. This new way of seeing how the universe began changes everything that we once believed about existence. Instead of thinking of creation as a single moment that happened billions of years ago, we now see it as a continuing process. We see it as a never-ending cycle of birth and destruction that unfolds in the hidden world of quantum physics. In this mysterious realm, the line between nothing and something is not as simple as we once thought. In fact, what looks like an empty space is not empty at all. It is filled with an unseen energy, just waiting for the right conditions to bring something new into existence. With this view, the birth of our universe was not a one-time event. It was part of an endless rhythm of creation. Imagine an unseen cosmic dance where the chance for new worlds exists in every single moment. What scientists call the quantum vacuum, which is often thought of as a vast empty void, is really a restless sea of energy. It is constantly bubbling with activity. Even the tiniest shifts in energy can spark the birth of whole galaxies, stars, and planets. In the study of the universe, there is an interesting idea called cosmic inflation. It is also known as cosmological inflation, or simply inflation. This idea says that in the very first moments of existence, the universe grew at an unbelievably fast rate. It grew much faster than it does today. Think of a tiny dot suddenly stretching into something millions and millions of times bigger in the blink of an eye. This took place right after the Big Bang, laying the base for everything that we see today. After this sudden inflation ended, the universe kept on growing, but at a much slower speed. Then something even stranger happened. More than 7,700,000,000 years after the universe was born, this growth began to speed up again. This was about 5,400,000,000 years ago. Scientists believe that this is because of a mysterious force called dark energy. This force is still not fully understood. The idea of cosmic inflation was developed between the late 1970s and the early 1980s. Several well-known physicists worked on it. These included Alexei Starobinsky from the Landau Institute for Theoretical Physics and Alan Guth from Cornell University, and Andrei Linde from the Lebedev Physical Institute. Their work was so important that in 2014 they received the Kavli Prize for starting this theory. But why is inflation important? One of the biggest mysteries in the study of the universe is how the large structures of space came to exist. These structures include galaxies, clusters of galaxies, and the vast empty regions called cosmic voids. Inflation gives a possible answer. The tiny quantum ripples, the tiny changes in energy during this period of inflation, were stretched to huge sizes. Over time, these ripples became the seeds from which galaxies and other cosmic structures were formed. Physicists also think that inflation explains other strange features of the universe. It helps us understand why the universe looks almost the same in every direction, and why the cosmic microwave background radiation is spread out so evenly. It also explains why the universe looks flat instead of curved, and why scientists have never found unusual particles called magnetic monopoles. Some earlier theories said these particles should exist. Even though the idea of cosmic inflation is widely accepted, scientists still do not know exactly what started it. Some ideas suggest that a special kind of field called the inflaton field was responsible. This field might have created a force that made space grow faster than the speed of light for a short time. It did this before slowing down again. Many of the predictions of inflation have been supported by scientific studies. For example, in 1992, the COBE satellite found tiny temperature differences in the cosmic microwave background radiation. This was just as inflation theory had predicted. Later, the WMAP satellite gave even stronger proof. However, not all scientists agree, and some of them still question whether inflation really happened. The idea that the universe is growing larger goes back to the early 1930s. This was when the astronomer Edwin Hubble made an important discovery. He found that light coming from faraway galaxies was redshifted. This meant that the galaxies were moving away from us. Even more interesting, the farther away a galaxy was, the faster it was moving. This meant that the universe was not fixed, it was stretching and expanding. But even before Hubble's discovery, two scientists had already predicted that the universe should be expanding. These were Alexander Friedmann and Georges Lemaitre. They made this prediction based on Einstein's general theory of relativity. They suggested that a powerful push at the start had sent everything outward, and gravity had never been strong enough to stop it. Cosmic inflation might be the missing piece of this puzzle. According to Friedmann's equations, a special kind of energy with a negative pressure could cause a powerful repelling effect. This would make space expand extremely fast. This kind of energy could have come from a quantum field in a false vacuum state. This is a state where energy is stuck at a higher level before dropping to a lower stable one. In 1979, the physicist Alan Guth put forward the idea that this inflationary growth could also explain something else. It could explain why certain unusual particles like magnetic monopoles have never been found. Inflation would have spread them out so much that they became incredibly rare. This solved a major problem in physics at that time. Scientists also realized that inflation solves two other major puzzles. The horizon problem: how is it possible that parts of the universe that are billions of light years apart look so much alike? Inflation says that they were once much closer together before expanding quickly. The flatness problem: why does space seem to be perfectly flat instead of curved? Inflation explains that the rapid expansion stretched out any curves, which is making the universe appear to be flat. Looking up at the night sky, there is a limit to how far we can see. This is not because something is blocking the view, but because the universe itself is expanding. Just like standing on Earth and seeing the horizon where land meets the sky, the universe has its own horizon. This is called the cosmological horizon. This marks the farthest distance from which light has had time to reach us since the universe began. Beyond this limit, space is stretching so fast that light from those areas will never reach us. The part of the universe that we can see is just a small piece of a much larger cosmos. There are regions that are so far away that no light or signals from them have ever reached Earth. These unseen regions lie beyond our current cosmological horizon. Scientists estimate this horizon to be about 46 billion light-years in every direction. In the standard view of the Big Bang, without adding extra ideas, the cosmological horizon grows over time. It shows us new areas of space. But here is a puzzling problem. Whenever we see a new area for the first time, it looks almost the same as the rest. Its background radiation, a faint glow left over from the Big Bang, has almost the same temperature as everywhere else. Its space-time shape, or the way that gravity bends space, also matches the rest of the universe. How is this possible? How did these far-off regions know what temperature and shape to have when they were never connected before? This is where the theory of inflation helps. Inflation says that in the very early universe, space grew at an incredibly fast, nearly unimaginable rate. This was because of a powerful energy field, sometimes called a vacuum energy, or a cosmological constant. Unlike normal growth, this process kept the cosmological horizon at a fixed distance. This meant that parts of space were quickly pushed apart, stopping them from staying in contact. But since they all began in the same small uniform space, they kept the same temperature and shape. They kept them even after being stretched across the universe. As inflation slowed and this special energy faded, the universe switched to a slower growth. The regions that were pushed beyond our view slowly came back into sight. They looked exactly as they had before, keeping their nearly identical temperatures and shapes. This explains why the universe looks so even in places that were never connected. The theory of inflation makes another interesting prediction. It says that the overall shape of the universe should be perfectly flat. This means that the total amount of normal matter, dark matter, and leftover energy in space must add up to a precise value. This value is called the critical density. Studies confirm that this is true. Inflation also helps scientists predict the tiny temperature changes across the sky. These were caused by the small quantum ripples that happen during this fast growth. Many of these predictions have been tested and confirmed, giving strong support to the theory. In a universe that grows faster and faster, objects that start close to each other will slowly drift apart. They will drift more and more unless a force like gravity holds them together. From the view of one object, the surrounding space acts like a black hole turned inside out. Anything that is crossing a certain line, its own event horizon, can never return, and even light from it will never come back. This kind of endlessly growing space is called the de Sitter space. For it to exist, there must be a special energy known as the cosmological constant. This energy stays the same over time and keeps space from slowing down. When space grows at an exactly exponential rate, this vacuum energy makes a type of pressure. This pressure perfectly balances its energy level. However, in most inflation models, the growth is not perfectly exponential. It is a little slower. This means that the horizon grows slowly over time as the vacuum energy slowly fades. This small difference allows scientists to make careful predictions about how inflation shaped the early universe. Many of these predictions match what we see today. When the universe was very young, it went through a sudden period of fast growth called inflation. One of the most important effects of this growth was that it stretched out any differences in temperature or density. This made everything more even. In simple terms, inflation smoothed out any bumps. It made the universe almost the same in every direction, and it reduced any natural curves that it might have had. At this time, the universe was almost completely controlled by a mysterious force field. This was known as the inflaton field. The only small differences that remained were the tiny quantum ripples. These were minute changes that later helped to form galaxies and other structures. Another result of inflation was that it greatly reduced the number of unusual heavy particles. These include magnetic monopoles, the rare particles predicted by some physics theories. If the universe had ever been hot enough to create these particles before inflation began, they would have been spread out. They would be spread out so much that finding even one of them today would be extremely unlikely. Scientists call these effects the no-hair rule of inflation. This is an idea borrowed from black hole science. The simple idea is that just like black holes eventually lose all unique features, the universe after inflation lost almost all signs of its earlier complexity. The unique features of a black hole are its mass charge and spin. The universe was left in a plain, smooth, and nearly empty state. Inflation made the universe grow by a huge amount in a very short time. As space grew, the density of most forms of energy went down. This was because they became more spread out. For example, the thickness of normal matter like dust fell by a factor of 8 when the universe doubled in size. Radiation such as light lost energy even faster. This is because, in addition to spreading out its waves, also stretched, causing a redshift. When the universe doubled in size, the energy thickness of radiation dropped by a factor of 16. But during inflation, the inflaton field kept almost the same energy level. Meanwhile, everything else had its energy spread out so much that it became unimportant. This included irregularities, curves, unusual particles, and even normal particles. This left the universe extremely even flat and mostly empty by the time inflation ended. Inflation was a time of extreme cooling. The temperature fell by an amazing factor of 100,000. In the first models of inflation, scientists guessed that the temperature dropped. It dropped from about 10 to the power of 27 Kelvin to about 10 to the power of 22 Kelvin. This freezing stage lasted all through inflation. But once inflation ended, the universe's temperature rose sharply again. This process is called reheating or warming. It happened as the great energy stored in the inflaton field turned into normal particles. These are the particles that make up atoms and electromagnetic radiation. This marked the start of the universe's radiation-filled age. Even though inflation theory explains many things about the early universe, there are still unknowns. Scientists do not fully know what the inflaton field is made of, nor do they know exactly how reheating happened. However, some of them think that it happened through a process called parametric resonance. In this process, energy moved in a very fast and highly effective way. Back in the 1970s, scientists found many strange issues with the Big Bang theory. To solve these puzzles, the physicist Alan Guth came up with the idea of cosmic inflation in 1979. His research began with a simple question: why do we not see magnetic monopoles? These are made-up particles that should exist according to some physics ideas. Guth found that if space had a special kind of energy called a false vacuum, it would start an incredibly fast growth. This would be an exponential stretching of space itself. Very quickly, scientists saw that this could explain not just the magnetic monopole problem, it could also explain other deep mysteries of the universe. These mysteries all pointed to one strange fact. For the universe to look the way it does today, it had to start in a very exact, finely balanced state. Inflation gives a way for the universe to naturally reach this state. This makes a cosmos like ours much more likely under the Big Bang theory. One of the biggest puzzles in the study of the universe is called the horizon problem. This problem asks why the universe looks so even. Why are the galaxies spread out smoothly, and why is the cosmic background radiation having nearly the same temperature everywhere? To explain this, think of a container of gas. The gas spreads out evenly because the molecules have had time to mix and to balance their temperature. But the early universe did not have enough time to mix in this way. In the normal Big Bang model without inflation, the parts of space that are very far apart today were always too far apart to connect. They were moving away from each other faster than the speed of light. This means that they could never share heat or information. This makes it hard to explain why they ended up with almost the same temperatures. Scientists had tried other ideas before inflation. Georges Lemaitre and Richard C. Tolman suggested that the universe might have gone through many cycles. These would be cycles of growing and shrinking, giving it time to balance out. But their ideas ran into a problem, an entropy buildup. With each cycle, disorder would grow, which made their models fail. Another idea came from the physicist Charles W. Misner. He suggested a messy early universe, something called the Mixmaster model, that might have smoothed things out. But later studies showed that this would not actually fix the problem. Inflation, however, gives a simple and clear answer. It says that before the universe became the size that we see today, it went through a time of very fast growth. This means that the parts of space that are now billions of light years apart were once right next to each other. They had time to interact and to share heat, and then got stretched far apart. This is why the universe looks so even today. Another puzzle is called the flatness problem. When astronomers study the universe, they see that space is almost perfectly flat. This means that its overall shape follows the kind of geometry taught in school. In this geometry, parallel lines stay parallel, and the angles of a triangle always add up to 180 degrees. This is strange because over time the curve of space should have become much more noticeable. The density of matter in the universe is very close to the critical density. This is the exact amount needed for space to stay flat instead of curving into a ball or saddle shape. But in a universe without inflation, if we go back in time, this fine balance becomes more and more extreme. At the time of Big Bang nucleosynthesis, when the first atoms were formed, the curve had to be extremely precise. It had to be 1 part in 10 quadrillion, that is 16 zeros. Any small change from this balance in the early universe would have led to a very different outcome. The universe would have either grown too fast, stopping galaxies from forming, or collapsed in on itself. Inflation solves this by stretching space so quickly that any first curve gets smoothed out. This is just like blowing up a balloon, makes its surface look flatter. This explains why space today is so close to perfectly flat. According to a group of physics ideas called the Grand Unified Theories, or GUTS, the forces of nature were once joined. These forces are electricity and magnetism, the strong nuclear force and the weak nuclear force. They were joined into one single force in the very early universe. When the universe cooled down, this force broke apart like ice forming from water. But these ideas also predict the making of magnetic monopoles. These are particles that carry a one-sided magnetic pole, like a magnet that has only a north pole or only a south pole. These should have been made in huge numbers in the early universe. If that were true, they would be everywhere today. And yet we have never found even one of them. Inflation gives a simple fix. If the universe grew massively right after these particles were formed, it would have spread them so far apart. They would be almost impossible to find today, too few to detect. In other words, inflation spread them out of existence. But some scientists, including Martin Rees, have pointed out a funny problem with this idea. He said that critics might argue that it is easy to claim success in solving a problem when the problem itself might never have existed. Even so, inflation is still the best explanation for why we do not see these unusual particles today. In the early days of general relativity, Albert Einstein added a mathematical term. This was called the cosmological constant. He did this to make the universe appear to be still and unchanging. Many scientists at the time believed that it was. His model described the universe as a three-dimensional sphere filled evenly with matter, but the Dutch physicist Willem de Sitter later found a completely different answer. In his answer, the universe was growing fast because of the cosmological constant, but with no matter at all. Scientists later saw that Einstein's model was unstable. If even the smallest disturbance happened, it would either collapse or turn into a fast-growing de Sitter universe. Moving forward to the mid-1960s, a physicist named Ernst Gleiner came up with a bold idea. He suggested that in the early universe, pressure was not behaving the way scientists thought. Instead of pushing outward, the pressure was actually negative and directly linked to an energy density. This idea, though mostly ignored at the time, would later become the first hint pointing toward dark energy. This is the strange force that makes up most of our universe today. By the early 1970s, a problem with the Big Bang theory appeared. The Soviet physicist Yakov Zeldovich saw two major puzzles: the flatness problem, why the universe's overall shape looks nearly perfectly flat instead of curved, and the horizon problem, why far apart regions of the universe look so alike, even though they could never have interacted. Up until then, scientists thought that the universe's smoothness was just luck. In the Soviet Union, these puzzles led two physicists to study a messy math idea. These were Vladimir Belinsky and Isaac Kalatnikov. The idea was called the BKL singularity, a possible answer for the disorderly first moments of the universe. Meanwhile, in the United States, the physicist Charles W. Misner worked on the Mixmaster universe. This was a model that used chaotic motion to try to solve these cosmic puzzles, though only with limited success. Then came the late 1970s, when physicists turned to quantum mechanics. They used it to study how the universe might have begun. Sidney Coleman, an American physicist, used a math tool called instantons. These were developed by Alexander Polyakov and others. Coleman used them to explore how unstable states in quantum fields might suddenly switch to more stable ones. He realized that much like water needs a small ice crystal to start freezing, the universe might have needed a tiny bubble of true vacuum to begin its growth. But Coleman did not fully explore the role of gravity in this process, or its link to the growth of the cosmos. One of the boldest ideas in physics suggests that the universe might have come from nothing. No space, no time, and no matter. This would have happened because of quantum fluctuations, the tiny energy shifts that can suddenly create particles. In the years 1978 and 79, three physicists suggested something. These were Robert Brout, Francois Englert, and Edgard Gunzig. They suggested that our universe might have started as a random fluctuation in an empty space. This was followed by a stage where it grew like a de Sitter universe, before turning into the familiar expanding universe we see today. Their idea was groundbreaking because it suggested that the universe had no strict beginning in the usual sense. At the same time, another Soviet scientist, Alexei Starobinsky, suggested that quantum effects could play an important role. He suggested this for the early universe. He said that when space-time is curved strongly enough, quantum physics naturally creates something similar to a cosmological constant. This leads to a period of inflation where the universe grew extremely fast. His model not only solved the problems pointed out by Zeldovich, it also made predictions about the small changes in the cosmic microwave background. This is the faint glow left over from the Big Bang. Around 1978, Zeldovich noticed another big puzzle, the magnetic monopole problem. This was a more exact version of the horizon problem, but it applied specifically to particle physics. It suggested that there should be many unusual one-pole magnets in the universe, but none of them had ever been found. In 1980, the physicist Alan Guth realized that a rapid inflation in the early universe could explain this. It could explain why we do not see these magnetic monopoles. His idea was that the universe, as it cooled after the Big Bang, got stuck in a high-energy state. This was similar to how supercooled water can stay a liquid even below its freezing point. In time, this unstable state broke apart, setting off a rapid exponential growth known as inflation. At nearly the same time, another physicist, Demosthenes Kazanis, suggested that inflation could solve the horizon problem. Meanwhile, Katsuhiko Sato proposed that it could also remove exotic structures called domain walls. In 1981, Einhorn and Sato built on Guth's idea. They showed that it not only explained the absence of magnetic monopoles, but also other cosmic puzzles. However, their models required an extremely precise cosmological constant, and the rapid growth could have made the universe too uneven, creating extreme differences in density. Guth further developed his inflation model. He said that the early universe, as it cooled, was trapped in a state of false vacuum. This was a condition with a high energy similar to the cosmological constant that Einstein once suggested. In time, bubbles of true vacuum were formed, spreading quickly at the speed of light and wiping out the false vacuum. However, Guth soon saw a major problem. His model did not explain how the universe became filled with the heat and light that we see today. The bubble process alone was not enough to reheat the universe properly. For inflation to fully work, something had to create radiation. And in his first model, this could only happen if the bubbles collided. But if inflation lasted long enough to solve the first problems, then the bubbles would be so far apart. They would be so far apart that they would not collide often enough. This major problem in the early inflation models was called the bubble collision problem. It was later solved by André Linde and separately by Andreas Albrecht and Paul Steinhardt. They suggested a new version called new inflation, or slow roll inflation. This improved the earlier model by Alan Guth, which was now called old inflation. In Guth's first idea, inflation involved a sudden tunneling from a false vacuum state, but this led to problems with the bubbles colliding in a messy way. The new inflation model worked differently. Instead of a sudden tunneling, it said that inflation was driven by a scalar field. This field was slowly rolling down an energy slope like a ball rolling down a hill. As long as the slope was gentle, the universe expanded at an exponential rate. But as the slope became steeper, inflation ended, and a process called reheating began. This let energy turn into matter and radiation, setting the stage for the universe as we know it. Over time, scientists found that new inflation did not create a perfectly smooth universe. Instead, tiny quantum fluctuations appeared in the inflaton field. These small irregularities became the seeds for galaxies, stars, and all of the cosmic structures we see today. The first calculations of these fluctuations were made by Vyacheslav Mukhanov and G.V. Chibisov. They were studying a similar model suggested by Alexei Starobinsky. In the early 1980s, researchers at the Nuffield workshop on the very early universe also studied these fluctuations. This workshop was held at Cambridge University. The event, lasting 3 weeks in 1982, brought together leading physicists. They reached the same conclusion about the quantum fluctuations in inflation. Stephen Hawking, Alexei Starobinsky, and Alan Guth with So-Young Pai each worked separately. A team of James M. Bardeen, Paul Steinhardt, and Michael S. Turner also worked on this. They all worked to confirm these early fluctuations. Even with these problems, inflation theory was improved and became one of the most accepted explanations for how our universe began. Scientists still test and refine these ideas using observations to uncover the true start of space and time. The idea of cosmic inflation is now a key part of modern cosmology. It helps to explain why the universe looks the way it does, and why it seems the same in all directions, and why space looks so flat. This idea also solves puzzles, like why we do not see strange particles such as magnetic monopoles. Theories said these particles should exist. Since Alan Guth first suggested inflation in the late 20th century, scientists have found more and more evidence to support it. One of the strongest proofs comes from the Planck spacecraft's study of the cosmic microwave background. These observations show that the universe is extremely flat. It is flat with a margin of error of only 0.1%. They also show that the universe is almost perfectly even. Tiny changes happen only once in every 100,000 regions. Inflation theory says that the galaxies, stars, and other large structures we see today grew from small fluctuations. These were fluctuations in energy in the early universe. These fluctuations caused by quantum physics later grew larger because of gravity. Scientists describe these fluctuations as a nearly scale-free Gaussian random field. This means that they follow a pattern predicted by inflation. This pattern depends on just two key numbers. One sets the strength of the fluctuations. The other makes a slight adjustment from a perfectly uniform state. Another important prediction of inflation is the tensor to scalar ratio. This ratio tells how many gravitational waves are present compared to the fluctuations in energy. Simple inflation models suggest that this ratio should be close to 1/10. Another key part of inflation theory is that all of these early fluctuations should have been balanced. This condition was called thermal equilibrium. Observations from several space missions have confirmed this idea. These include Planck the Wilkinson, Microwave Anisotropy Probe, and the Sloan Digital Sky Survey. These studies show that the small irregularities in the cosmic microwave background match the predictions from inflation very closely. Scientists have also measured the spectral index. This is a number that shows how much the fluctuations differ from a perfect balance. If the universe had a perfect balance, this index would be exactly 1. The simplest inflation models predict a value between 9,200 and 9,800. And data from the Planck mission suggests a value of about 9,700. This is seen as strong proof for inflation. Over the years, researchers have built many versions of inflation theory. Each has slightly different predictions. Most of them, however, require very exact adjustments to match the observations. Even so, inflation remains valuable because it can predict the starting conditions of the universe. It does so with just two numbers, the spectral index and the fluctuation strength. These predictions stay true no matter the exact way that inflation happened. Sometimes new observations seem to question inflation. For example, early data from the WMAP mission hinted that the fluctuations might not be as even as expected, but later data showed that this was likely just a random effect. Another strange finding came from studies of the cosmic microwave background. These showed that some fluctuations lined up with the plane of the solar system. This was something that scientists did not expect. Some researchers suggested that this could be a sign of new physics, quantum effects, or even mistakes in analyzing the data. Scientists still test inflation theory with better measurements. One of the big focuses is on finding B modes. This is a pattern in the polarization of the cosmic microwave background that could give direct proof of gravitational waves. These would be gravitational waves from inflation. In March of 2014, a team using the BICEP 2 telescope said they had found these B modes. This pointed to strong proof for inflation. They estimated a tensor to scalar ratio between 1500 and 2700. But by June of that year, their confidence in the result dropped. And by January of 2015, the doubts grew stronger. By 2018, new data showed that the actual ratio was at most 600. This means that the earlier signal was likely false. Other upcoming tests could check inflation further. The Planck spacecraft might give more hints, but it is not clear if the signals will be strong enough to find. Another hopeful method is looking at 21 centimeter radiation. This radiation comes from neutral hydrogen before the first stars were born. This method could give an even clearer view of the universe's early shape, but there are still problems such as interference from radio signals on Earth and in space. This interference could make the measurements hard. When Alan Guth first shared his idea of cosmic inflation, some scientists had a thought. They thought that the inflaton, the field that causes inflation, was really the Higgs field. The Higgs field is what gives mass to the basic particles. But later studies suggested that this might not be true. One of the big problems with this idea is that it does not fully fit with the test results from particle physics. This is especially true at the electroweak scale. Because of this, many scientists started searching for other answers. Some of them turned to the Grand Unified Theories, or GUTS. These theories try to bring together the main forces of nature to find a better model for inflation. One of the biggest problems with inflation theory is something called fine-tuning. This means that for inflation to work, the starting conditions must be very exact. In the new inflation model, a rule called the slow roll conditions must be met. These rules require the inflaton field to have a very smooth and gentle slope. This is compared to the huge vacuum energy of the universe. The inflaton particles also need to have a very tiny mass. For inflation to work in this model, the universe must have a special type of scalar field. It must have an extremely flat slope, as well as carefully arranged starting points. Scientists have offered reasons for why this might be so. One possible reason involves scale invariant field theories. In these theories, a property called scale invariance is broken by very small quantum effects. Scale invariance means that the equations look the same at any size. This could explain why the inflationary field has such a flat slope. But this answer only works if the theory can be studied by using a math method called perturbation theory. The physicist André Linde suggested another idea called chaotic inflation. He said that inflation is not something that needs very special conditions. Instead, he argued that inflation could naturally happen in almost any universe that begins in a chaotic high-energy state. This universe would have a scalar field that has no limit to its energy. In this theory, the inflaton field takes on values greater than 1 Planck unit. This is the smallest useful unit in physics. This is why these models are often called large field models. The competing models like new inflation are called small field models. But this idea has its own problems. According to effective field theory, if the inflaton field reaches such high values, the theory's predictions may no longer work. This is because a process called renormalization could bring in big changes that break inflation. Renormalization is used to stop a quantum field theory from giving endless or useless results. Scientists still have not solved this problem, and some of them say that the small field models give a better answer. In these models, inflation happens at a much lower energy. While inflation depends a lot on quantum field theory and on an estimate of quantum gravity, it has not yet been fully joined with these theories. The physicist Robert Brandenberger pointed out another fine-tuning problem. The size of the tiny ripples in the universe that later became galaxies is directly tied to the energy level. This is the energy level at which inflation happened. This energy level is thought to be around 10 quadrillion giga-electronvolts. This is about 1,000th of the Planck energy. The issue is that the natural energy level in physics is usually the Planck scale, which is much higher. The fact that inflation happens at a much lower energy is sometimes seen as another fine-tuning issue. This is known as the hierarchy problem, but this is not often seen as a major flaw. This is because the energy level of inflation matches well with the level where the main forces of nature may come together. Many models suggest that inflation never fully stops in the whole universe. Instead, it goes on forever, in at least some parts. This happens because the parts of the universe that are inflating grow so quickly. They grow so quickly that they keep on making new inflating regions. If the switch from inflation to a normal non-inflating state is too slow, then the new inflating parts will appear faster than the old ones fade away. In such models, most of the universe's space at any moment is still inflating. This means that inflation never really ends on the larger scale. This leads to an amazing result, an endless and always growing multiverse. The idea of a multiverse has caused a strong debate among scientists. Some of them think that it is a natural result of inflation. Others say that it weakens the whole theory. The physicist Paul Steinhardt was one of the first minds behind inflation theory. He was also the first to suggest the idea of eternal inflation in the early 1980s. He said that once inflation starts, it can last forever. He explained how bubbles of non-inflating space could form inside the inflating universe. These bubbles would be filled with hot matter and radiation, but these bubbles would not grow fast enough to spread everywhere, so inflation would keep on going in the empty space around them. Later in the same decade, Alexander Vilenkin showed that eternal inflation is a common feature of many inflation models. This means that it would happen under many different conditions. In the new inflation models, the inflaton field is expected to roll down its slope like a ball rolling down a hill. But because of tiny quantum changes, it can sometimes jump back up, creating new inflating parts. Since these higher energy regions grow much faster than the lower energy ones, they usually take over the space of the universe. This means that in any model where the inflaton field has no upper limit, inflation will go on forever. But there is a math problem with this idea. While an inflationary space acts like the de Sitter space, a model of an expanding universe, it cannot stretch endlessly into the past. There must have been a start. Unlike the de Sitter space, an inflating universe would one day shrink into a singularity. This is a point of endless density. Because of this, scientists still need a strong theory to explain how the universe began. In eternal inflation, the inflating parts of the universe grow very fast. The non-inflating parts do not. This means that the inflating part is always much larger than the parts that have stopped inflating. But inflation does end in some regions, letting galaxies, stars, and planets form. One of the biggest debates in modern physics is how to measure the chances in the different regions of this possible multiverse. Some scientists say that since inflation keeps on going in most of the universe, we should expect it to never end. Others say that if we assume a local observer like us must exist to see the universe, then inflation must at some point stop. Some physicists think that the puzzle of eternal inflation can be solved. It can be solved by asking how much space existed before inflation began. Others say that this puzzle is a basic flaw in inflation theory. Strangely, Paul Steinhardt, who first helped create the idea of eternal inflation, later became one of its strongest critics. He became a critic for this reason. Some scientists have tried to avoid the problem of explaining how the universe began. They have done this by saying that it never had a beginning at all. Instead, they suggest that the universe has always existed, still exists, and will never stop existing. According to these ideas, the universe is endlessly large, and it has been spreading out faster and faster forever. Other theories suggest that the universe came from nothing. These theories are based on ideas from quantum physics and cosmic inflation. One such idea was suggested by the physicist Alexander Vilenkin. Stephen Hawking and James Hartle offered a different one called the no-boundary idea. Their model says that the universe naturally went through an inflation right after it appeared. It did so without needing a clear starting point. The physicist Alan Guth called cosmic inflation the ultimate free lunch. He said that new universes like our own are always forming inside a huge, ever-growing cosmic background. In this picture, gravity plays a special role. It bends the usual rules of physics but does not break them. Normally, physics says that energy must be saved, and that disorder or entropy must always grow. But Guth's idea says that gravity allows for an exception. This makes new universes without breaking these main rules. Still, some scientists doubt this. One of them, Don N. Page, said that inflation may not really solve the problem of the universe's starting point. Instead, he thought that it made things harder. He said that for the universe to follow the rules of thermodynamics, it would have needed to begin in a very organized, low-entropy state. This case is very unlikely. If inflation did happen, it would have raised entropy even more. This means that the universe's first state would have needed to be even more orderly than the older Big Bang models suggest. This puzzle led some of them to ask whether inflation really explains the start of the universe, or does it just make the mystery deeper? Later, when Hawking and Page tried to work out how likely it was for inflation to have happened, they got unclear answers. Some scientists say that this does not matter because once inflation begins, it lasts forever. As long as the chance of inflation happening is not exactly zero, it would sooner or later take over the universe. Others, like the physicists Andreas Albrecht and Lorenzo Sorbo, said that an inflationary universe was much more likely than one without inflation. They argued that inflation needs much less starting energy to begin compared to a model where inflation never happens. This makes it the more likely case. Another problem, known as the trans-Planckian problem, comes from the fact that inflation happened at energy levels that were not far from the smallest possible scale in physics, the Planck scale. Some scientists say that before inflation, the quantum ripples in space were so tiny that they were smaller than the Planck length. If this is true, then the unknown laws of quantum gravity might have shaped how the early universe began. The effect of this is still argued about. Some of them think that these effects are too small to notice. Others think that they could be important. A version of inflation called hybrid inflation builds on an earlier idea. This idea was known as new inflation. It brings in extra energy fields. One field controls the universe's growth. Another decides when inflation ends. In this model, inflation does not go on forever. Instead, after lasting long enough, one of these fields reaches a point. At this point, it suddenly makes inflation stop. This lets the universe keep changing in a new phase. This idea of inflation is somewhat like the strange force called dark energy. This force is now making the universe grow at a faster and faster rate. But dark energy works at a much lower energy level. This is about 10 to the power of negative 12 giga-electron volts. This is about 27 steps lower than the energy level where inflation happened. A big step forward came with the finding of flux compactifications. This helped to connect inflation to string theory. One form of this idea was called brane inflation. It says that inflation happens when special objects in string theory, called D-branes, move through hidden dimensions. These branes meet with anti-D-branes, setting off an inflation in a way that is different from the older models. But scientists still do not fully understand how this works. It looks like inflation here happens through a process like old inflation. In this process, the universe shifts from one state to another by quantum tunneling. After that, another process must take over to finish inflation. Another idea comes from a field called loop quantum gravity. This field says that space itself is made of tiny, separate pieces. In this idea, if the energy of the universe ever grows too high for this chunked space to hold it, the universe could bounce. It could bounce instead of falling in on itself. This gives another possible answer for how inflation began. Even though these theories explore different paths, they all try to answer one of the biggest questions in science. How did the universe begin, and what forces shaped its growth? Scientists have suggested different ideas to explain the mysteries of the early universe. Some of these give other options to the widely accepted idea of cosmic inflation. One such idea is the Big Bounce theory. This says that instead of the universe starting from an endlessly small and heavy point, a singularity, it first went through a time of shrinking. Then it suddenly started growing again. This bounce gives an answer for the conditions that led to the Big Bang. It naturally solves two big puzzles in space science. These are the flatness problem, why the universe looks so smooth and even on big scales, and the horizon problem, why different parts of the universe which should never have touched still look the same. This answer comes from a changed version of Einstein's theory of gravity. This is called the Einstein-Cartan-Sciama-Kibble theory. Unlike normal general relativity, this theory adds an extra factor called torsion. This factor changes how particles act in extreme states. Put simply, when the universe was very dense, torsion made a force. This force stopped it from shrinking into an endlessly small point. Instead of a singularity, there was a smallest size before the universe bounced back into growth. This early fast growth explains why the universe now looks flat, smooth, and even on the bigger scales. As time went on and the universe spread out, the effects of torsion faded. This led to the radiation-filled phase that we see in early space history. Another group of ideas are called the ekpyrotic and cyclic models. These give a different answer. They say that the universe goes through endless cycles of growth and shrinking. Long before the Big Bang, the universe was already growing, which helps to explain the horizon problem. Then, during a shrinking time, the universe collapsed into a big crunch, only to be born again in a hot Big Bang phase. This cycle goes on without an end. These ideas are like an older thought from the early 20th century. This thought was called the oscillating universe, suggested by Richard Chase Tolman. But unlike Tolman's idea, which said the universe had a limited life, the modern cyclic models allow for a forever universe, a universe with no start or end. One of the problems for these models is whether they can explain the tiny changes in density. These were the changes in the early universe that later made the galaxies. There is also a debate about whether the universe can really move from a big crunch to a big bang, and do so without breaking the known laws of physics. One possible strength of these models is that they avoid the magnetic monopole problem. This is a problem in physics where certain expected particles have never been found. This only works if the heat at the Big Crunch stays below a key level. This level is called the Grand Unified Scale, which is needed to make these missing particles. If the cyclic model is right, we would not yet see proof of the universe slowing down. This is because each cycle is thought to last about 1 trillion years. Another option to inflation comes from string theory. This theory says that besides the 3 dimensions of space, we know hidden extra dimensions exist. These extra dimensions are thought to be very small and curled up. This makes them unseen in daily life. This idea appears in supergravity models and other theories. These theories try to join quantum mechanics and gravity. A thought called string gas cosmology was put forward by Robert Brandenburger and Kumrun Vafa. It tries to explain why only 3 dimensions grew large while the others stayed curled up. Their idea imagines the early universe as a hot gas filled with tiny shaking strings. These are the basic building blocks of nature in string theory. These strings can wrap around the extra dimensions, and for a dimension to grow, the strings wrapped around it must be able to cancel each other out. Their math shows that this works best in exactly 3 large space dimensions. This matches what we see today. Scientists are still working to improve this idea. They are especially trying to see if it can explain the tiny changes in matter that made the galaxies. The first version of the theory did not fully solve some of the big space problems, but later changes that added the bouncing universe idea have helped to fix these issues. Yet another idea questions a basic law of physics, the speed of light. Some researchers say that in the very early universe, light moved much faster than it does now. This is called the variable speed of light theory. If it is true, it would mean that different parts of the universe could have shared information and energy more easily. This would solve the horizon problem without needing inflation. In this idea, as the universe grew, the speed of light slowly fell to the value we see today. These other theories give amazing possibilities for understanding how the universe began. While none of them have yet taken the place of inflation as the main answer, ongoing research keeps looking. It keeps looking into whether any of them might fit the cosmic puzzle better. For as long as people have looked up at the night sky, one big question has always stayed in their minds. Are we really alone? Is Earth the only place in this huge, endless universe where life can exist? Or could there be other worlds hidden among the stars where living beings thrive just like us? This puzzle has fascinated thinkers, scientists, and dreamers for thousands of years. It is a question that challenges everything we believe we know about life, space, and the very meaning of existence itself. Now, thanks to very powerful telescopes and important new scientific discoveries, we are closer than ever to finding the truth. The search for life beyond Earth, which is called the hunt for life in space, is one of the most exciting and important quests in modern science. It takes us far beyond the edges of our own solar system to faraway exoplanets. These are the planets that go around stars many light years away from the Sun. It also makes us look at our own solar system in new ways. It makes us search its hidden places for signs of life. As scientists go deeper into this great puzzle, they are also rethinking what life is and what it truly means to be alive. One of the biggest questions that scientists are trying to answer is what makes a planet able to support life. Earth is full of life in every form imaginable, from the tiniest germs to giant trees and enormous sea animals. But why is our planet so special? What conditions make life possible here? And could those same conditions exist on other planets? A key need for life, at least as we understand it, is liquid water. Every living thing on Earth needs water to survive. It helps to break down substances, making it possible for chemical changes to happen. Water also carries food materials, helps to keep temperatures steady, and supports the basic parts inside cells. Without water, life as we know it could not exist. But why does Earth have liquid water while other planets do not? The answer lies in Earth's special position in space. Our planet sits in a very special area around the Sun called the habitable zone. This is the perfect distance where the temperatures are just right, not too hot and not too cold, so that water can stay a liquid. Planets that are too close to their stars, like Venus, are so hot that any water on their surface boils away. Planets that are too far, like Mars, are so cold that water turns to ice. But Earth sits in the perfect spot. This allows lakes, rivers, and oceans to exist, which makes life possible. However, water alone is not enough. Life also needs a source of energy. On Earth, the main source of energy is the sun. Plants use sunlight to make food through a process called photosynthesis. Then animals eat the plants or other animals to get the energy they need to live. The sun's energy powers every part of life, from the smallest plants to the largest predators. But what if life could survive without sunlight? Scientists have found that deep in Earth's oceans, far beyond where sunlight can reach, strange creatures live. They live near underwater vents. These are openings on the ocean floor that release heat and chemicals from below Earth's crust. The creatures living there do not use sunlight at all. Instead, they use the heat and chemicals from these vents to make energy. This shows that life can exist in conditions that are very different from those on Earth's surface. This discovery has completely changed how we think about life in the universe. If life can survive in such extreme places on Earth, then could it also exist on faraway planets or moons with similar conditions? Some scientists believe that places like Europa, a moon of Jupiter, or Enceladus, a moon of Saturn, could be home to alien life. These icy moons are thought to have huge oceans hidden beneath their frozen shells. If heat from their cores provides energy just like the vents do on Earth, then maybe life could be growing. It could be growing in those dark alien waters. But for life to form and to change over time, it needs more than just water and energy. It needs steadiness. A planet or moon must have the right conditions for millions or even billions of years for life to grow. Think of it like planting a tree. If the soil, sunlight, and water keep changing too much, the tree will not survive. In the same way, Earth has stayed steady long enough for life to grow and to thrive. But what about other worlds? Could they also offer the right conditions for life to change and to evolve? The search for life beyond Earth is not just about finding alien creatures, it is about understanding our place in the universe. If we find even the tiniest germ on another planet, it would change everything. It would prove that life is not unique to Earth, and that the universe is full of possibilities, and that somewhere far beyond the stars, we may not be alone after all. One of the most important gifts that Earth gives to all living things is its air layer called the atmosphere. This invisible cover that surrounds our planet plays several key roles. First, it protects us from the harmful rays coming from space which would otherwise be deadly. Second, it helps to keep a steady climate by holding in heat and stopping extreme temperature swings. And third, it acts as a shield against the strong solar winds that could strip away our planet's surface. Without this protective cover, Earth would be an icy, empty wasteland. It would be constantly hit by deadly radiation, a place where life as we know it could not survive. Now think about what it would take for another planet to support life. For a world to allow living creatures, it would need an air layer that protects against space radiation. It would also need a way to control temperature so that it does not get too hot or too cold. And it would need a strong magnetic field to push away harmful solar winds. These are the same things that make Earth livable. Without them, any planet would be left open to the harshness of space. This would make it almost impossible for life to grow. This brings us to an amazing question. How many planets out there have the same life-friendly conditions as Earth? Could there be other worlds where life has started and grown just as it did here? To explore this, scientists use an idea known as the Drake equation. This math formula was created by the astronomer Frank Drake in 1961. It is meant to guess how many smart civilizations in our galaxy might be able to talk with us. Instead of giving a direct answer, the formula helps to break the problem into smaller parts. Each part asks about a different thing that could affect whether alien life exists. The Drake equation asks several key questions. For example, how many stars in our galaxy have planets? Out of those, how many planets have the right conditions for life? Among those, how many might produce intelligent beings? And of the planets with intelligent life, how many civilizations would grow advanced enough? How many would make technology that lets them send signals across space? Even though the Drake equation does not give a clear answer, it serves as a guide. It helps scientists to organize their search for alien life. It reminds us that many things must come together for a civilization to exist and to be found. But here is the great puzzle. If life is common in the universe, then why have we not heard from anyone yet? This question is called the Fermi paradox. We know that the conditions for life might exist beyond Earth, and yet after years of searching, we have found no signs of other civilizations. Scientists and thinkers around the world continue to wonder about this. Where is everyone? If intelligent beings are out there, then why have they not reached out? In 1950, the physicist Enrico Fermi famously asked, "Where is everybody?" His question was based on a simple but powerful thought. If the universe is so huge and filled with countless stars and planets, and if intelligent life is likely, then why have we not found any alien civilizations? This clash between the high chance of life existing elsewhere and the total lack of proof is what we now call the Fermi paradox. The paradox makes us face an uneasy truth. With billions of planets spread across the universe, it seems fair to expect something. At least some of them should host intelligent beings. And yet, despite our best efforts, we have found no messages, no radio signals, and no traces of advanced alien societies. The silence is overwhelming. There are many possible reasons for this, but none of them are proven. One idea is that intelligent civilizations are very rare, which makes it almost impossible to find them. Another idea is that while life may be common, very few species ever develop advanced tools. Maybe most civilizations destroy themselves before they reach a stage where they can communicate across space. This could be through war, environmental collapse, or other disasters. For many years, scientists have been searching for signs of intelligent life beyond Earth. Some of them believe that these advanced groups might be so incredibly far away that their signals have not reached us yet. Others suggest that the huge distances between us make it nearly impossible to detect them. Another idea is that these civilizations are purposely avoiding us, maybe for their own safety, for moral reasons, or simply because they do not want to contact a less advanced species. Even with these challenges, the search for alien life continues. Scientists remain hopeful that one day we will find clear proof that we are not alone in the universe. If we were to discover an intelligent alien life, it would be one of the most amazing and history-changing moments of all time. It would completely change how we understand the universe and our place in it. Even though we have not yet found aliens, our journey to find the truth has already led to amazing discoveries. These are discoveries about space and even about ourselves. This search for alien life is not limited to one country or a small group of researchers. It is a worldwide effort. Scientists from all over the globe are working together. They are using some of the most advanced tools available to scan the skies for any signs of alien intelligence. One of the main tools used in this search is the radio telescope. These giant instruments are made to detect very specific signals called narrowband radio signals. These signals are very exact and focused. This makes them unlikely to come from natural things like stars or planets. Instead, they could be a sign of an advanced group trying to talk across space. While no confirmed alien signals have been found, yet scientists are not giving up. They continue to make their equipment better, making it more sensitive and able to scan larger parts of the sky. This raises the chances of finding something amazing. But the search for alien life is not just about listening for signals. It also means looking for planets beyond our solar system that might support life. Space missions like Kepler and TESS have helped astronomers find thousands of exoplanets. This shows that planets are far more common in the universe than we once thought. In fact, there are likely more planets than stars in our galaxy. Some of these exoplanets are in what scientists call the habitable zone. This is a region around a star where conditions might be just right for liquid water to exist. Since water is needed for life, as we know it, planets in this zone are considered the best candidates for hosting alien life. Every new discovery brings scientists closer to finding a planet with the right conditions for life. But while we search the far corners of the universe, there are also amazing possibilities much closer to home. Some of the best places to look for alien life may not be on distant planets. They may be on the moons right here in our own solar system. Two of the most exciting places for possible alien life are Europa and Enceladus. These are the moons of Jupiter and Saturn. At a first glance, these frozen worlds might seem lifeless and unwelcoming. However, beneath their thick layers of ice, scientists believe there are huge oceans of liquid water. These hidden oceans could provide the perfect place for life to exist, even in extreme conditions. Water is one of the most important parts of life, and these underground oceans might have everything needed to support living creatures. Europa, in particular, has caught the interest of scientists for many years. NASA is preparing to launch the Europa Clipper mission soon. This mission will study the moon closely. This spacecraft will look for signs of life beneath Europa's icy surface. It will study its ocean, its ice, and its other features. Scientists are especially interested to see if the conditions on Europa are like the deep sea areas on Earth. These are areas where strange and tough creatures live without sunlight. Enceladus is another exciting choice for hosting life. In 2005, NASA's Cassini spacecraft made a groundbreaking discovery. It found that Enceladus was shooting huge plumes of water vapor into space. These plumes suggest that there is a vast liquid ocean beneath the ice, and they might contain the chemicals needed for life. If tiny microorganisms exist in these hidden waters, it would be an amazing breakthrough. It would prove that life can exist beyond Earth. What makes these icy moons so exciting is that they could help us understand how life might survive. How life might survive in the harshest places. If life can exist in the dark, hidden oceans of Europa or Enceladus, then it is possible. It is possible that similar conditions exist on other moons or planets across the universe. This could completely change how we think about the search for alien life. It could lead us to look beyond Earth-like planets and to consider totally new possibilities. The search for life beyond Earth is one of the most exciting and deep challenges that humanity has ever faced. It makes us question everything we know about life, the universe, and our own existence. Are we truly alone in the cosmos, or is there something or someone out there waiting to be found? Every time we detect a strange signal, find a new planet, or uncover proof of a hidden ocean, we take one step closer. We take one step closer to answering that ultimate question. The anthropic principle is an idea in the study of the universe. It says that the universe must have the right conditions for life, because if it did not, then no one would be here to see it. In simple terms, the universe looks to be perfectly set up for life only because a universe that could not support life would never have thinking beings around to ask about it. The people who support the anthropic principle believe that this idea helps to explain something. It helps to explain why the universe has a certain age and certain unchanging numbers that make life possible. If these numbers were even a little different, intelligent life might never have appeared. For example, if the universe were much younger, there would not have been enough time for stars to make the heavier elements needed for planets and living things. If it were much older, most stars would have burned out, and star systems like ours might not exist. Scientists have long asked why the basic physical numbers are exactly what they are. These are the fixed values that guide physics. The anthropic principle says that they must be this way. They must be this way because only a universe with these conditions could support life. It is not that the universe was made for life, but it is that life could only arise in a universe with the right setup. There are many ways to understand the anthropic principle. Some thinkers, like the philosopher Nick Bostrom, have listed about 30 different versions of it. Still, they usually fit into two main groups: the weak anthropic principle. This says that we see a universe that is fit for life because life only appears in such a universe. The strong anthropic principle. This says that the universe must in some way be shaped to bring about life. The idea came from noticing that the universe's laws and numbers seem to be perfectly suited for life. It is an argument based on looking back. If the universe could not support life, we would not be here to talk about it. Some people say that calling it the anthropic principle is misleading. The word comes from the Greek word anthropos, which means human, but the idea does not say that the universe is made just for humans. Instead, it can apply to any form of life, not only humans or carbon-based creatures. It would work just as well for alien life stars or even galaxies. The anthropic principle has led to debates mainly because different versions of it have been used to argue different things. Some critics feel that the principle stops a deeper scientific study. For example, the weak anthropic principle is sometimes seen as unscientific because it cannot be tested or proven false. On the other hand, the stronger versions make bold claims that are still argued over. They are argued over because they rely on evidence that is hard to check. In 1961, the physicist Robert H. Dicke said that the universe must have a certain age that is fit for life. If it were 1/10 of its current age, elements like carbon would not have had time to form, and planets like Earth would not exist. If the universe were 10 times older, most stars would already be dead. They would leave behind mainly white dwarfs and faint red stars. This makes it unlikely for star systems to survive. Dicke also said that the universe's matter must be close to a critical density, just enough to stop it from collapsing in a big crunch, but not so much that it would prevent it from expanding. Later studies showed that normal matter makes up about 30% of this critical density. The rest is probably due to dark energy. In the late 20th century, the physicist Steven Weinberg gave an anthropic reason for the strange cosmological constant. This is a number that controls how fast the universe expands. The predicted value of this constant from particle physics is far off from the one we actually see. It is off by about 120 orders of magnitude. This has been called the worst prediction in physics. But Weinberg pointed out that if the cosmological constant were just a little larger, the universe would have expanded too fast. It would have expanded too fast for stars and planets to form, and without them, there would be no life. Some scientists say that the physical numbers that control the 4 basic forces of nature seem to be perfectly balanced. These forces are gravity, electromagnetism, and the strong and weak nuclear forces. The numbers seem balanced to let life exist. If, for example, the strong nuclear force were increased by just 50%, it would change the way elements form in stars. This would stop the creation of hydrogen, the key part of water and life as we know it. In the same way, small changes in the other forces would greatly affect the universe's age, its shape, and its ability to support life. The name anthropic principle was first used by Brandon Carter, a physicist. He used it at a 1973 meeting honoring the 500th birthday of Copernicus. Carter brought up the idea as an answer to the Copernican principle. The Copernican principle says that humans do not have a special or central place in the universe. Carter suggested that even though humans are not the center of the universe, the conditions we see must still be somewhat special. They must be special because they allow intelligent life to exist. At that time, the steady-state theory was still popular. This theory said that the universe always looked the same and had no beginning. But this theory was overturned in 1965 with the finding of the cosmic microwave background radiation. This was clear proof that the universe has changed over time, most likely starting with the Big Bang. In 1973, the physicist Brandon Carter explained 2 ideas under what he called the anthropic principle. The first, called the weak anthropic principle, said that humans only exist in certain times and places in the universe. This is because those places happen to be fit for life. The second, the more debated idea, was the strong anthropic principle. It went further. It said that the basic numbers of physics, the ones that shape the universe, might be set in a way that makes life possible. At first, the weak version seems to be reasonable. After all, humans could have developed in many different times and places as long as the conditions were right, but the strong version is harder to explain. There is only one known universe, with fixed physical laws. So why do those laws allow life at all? Carter gave 2 possible answers. First, humans can make good guesses about the physical numbers of the universe. They can do this based on the fact that they exist within it. But if that does not seem to be enough, then there is another answer. Maybe there is not just one universe. Maybe there are many, perhaps an endless number, each with its own physical laws. This idea is now called the multiverse theory, though Carter first called it the world ensemble. It would mean that our universe is only one among countless others, and we happen to live in one that allows life. This idea is daring, even radical, but it may help to explain a deep puzzle. Why do the laws of physics seem to be so perfectly balanced for life? If there are countless universes, most of them would not allow life, but a few of them would. Naturally, humans would only exist in one of the just right universes, so it should not surprise us that we live in one. Since Carter's paper, the anthropic principle has taken on many different meanings. A big turning point came in 1986. This was when the scientists John D. Barrow and Frank J. Tipler gave new versions of the weak and strong anthropic principles. These were different from Carter's original ideas, which caused confusion among scientists, but Carter was not the first person to think about such ideas. As early as 1904, the evolutionary biologist Alfred Russel Wallace suggested something. He suggested that the universe might need to be as huge and complex as it is in order to make a world able to support human life. Then in 1957, the physicist Robert H. Dick said that the age of the universe is not random. The living conditions decide why we exist at this point in cosmic history. He also said that if the basic numbers of physics were even slightly different, humans would never have existed to ask these questions. Even before these scientists, the Austrian physicist Ludwig Boltzmann had thought about similar ideas. This was in the late 19th century. Boltzmann wondered why the universe seemed to have such a low entropy, a measure of disorder. He wondered this when the rules of thermodynamics said it should be much more chaotic. He suggested that random changes could create short-lived pockets of low entropy. These are small areas where order briefly appears out of chaos. He argued that humans happen to exist in one of these rare, orderly areas. We exist there simply because that is the only kind of place where intelligent life could arise. Carter's version of the anthropic principle has led to much debate. This is partly because it is based on a simple but easy to misunderstand idea. The universe seems to be fine-tuned for life, so maybe it really is. Scientists such as Stephen Hawking and Michael Collins said that this might mean there is not just one universe. It might mean there is an endless number of universes, each with different starting conditions. If this is true, then the reason our universe looks so finely balanced is simple. We would not be here to notice it otherwise. Most universes would not allow life. But in an endless multiverse, at least a few of them would, and ours is one of them. Though scientists have wondered about similar ideas for hundreds of years, by the early 1970s, there was only one scientific theory that allowed for many universes. This was the many worlds interpretation of quantum physics. This theory says that every quantum event creates branching timelines, but it does not allow for changes in the basic physical constants. Since then, however, new theories have appeared. In the 1980s, a mix of inflation theory and symmetry breaking in the early universe gave a possible way. It gave a way for physical constants to change across different parts of space. By the early 21st century, string theory suggested an even more striking idea. What if every basic constant could change across an unimaginably huge landscape of possible universes? This includes the number of space dimensions. This idea is very different from the old goal of scientists to find one complete theory of everything, a theory with no free choices. Albert Einstein once asked whether God had any choice in setting the laws of physics. In other words, was the universe meant to be exactly the way it is, or could it have been different? In 2002, some scientists working on string theory believed they were close to removing the need for the anthropic principle. But by the next year, the scientist Leonard Susskind argued that the opposite might be true. He argued that the great complexity of the landscape of possible universes actually made the anthropic principle seem more believable than ever. The anthropic principle also plays a part in debates about intelligent design. Believers in intelligent design often point to the fine-tuning of the universe as proof of a creator. The critics, however, say that fine-tuning may not be as amazing as it looks. Some of them think that the universe is not really as finely tuned as people claim. Others suggest that even if it is, this does not clearly prove the existence of a higher power. Some of them even argue that the anthropic principle itself weakens the case for intelligent design. It does so because it gives another reason for why the universe supports life. Brandon Carter's weak anthropic principle is not something that can be tested through direct observation. It is more of a guiding idea for scientists. The strong anthropic principle, on the other hand, says that the universe is somehow required to support life. Testing this would mean finding proof of life in other universes. But since most meanings of universe say that we cannot see the others, this creates a big problem. The theory might be impossible to prove or to disprove. The thinker John Leslie once made a set of predictions based on the strong anthropic principle. He said that the laws of physics will turn out to be set by chance instead of strict necessity. He also said that theories about many universes will keep on gaining scientific support. More proof of fine-tuning in the universe will continue to build up. No forms of life based on non-carbon chemistry will ever be found, and mathematical studies of galaxy formation will show that the universe's expansion rate is crucial for shaping its structure. Some scientists like Craig Hogan say that it would be very strange if all basic constants were locked in place. This is because that would leave no way to explain fine-tuning. If that were the case, humans might be forced to accept that the universe simply had to be this way. It had to be this way to support life, whether we like it or not. The well-known astronomer Fred Hoyle may have used a special way of thinking called anthropic reasoning. He may have used it to make an amazing guess about the stars. He saw that life on Earth depends on a chemical element called carbon. Specifically, it depends on a type known as carbon-12. Since carbon is so important for life, he thought there must be an unknown process inside stars, a process that makes it easier for carbon-12 to form. He studied a particular reaction in stars called the triple alpha process. This process creates carbon from smaller helium atoms. Based on this idea, Hoyle guessed that there must be a hidden energy level or a resonance in carbon-12. This would make this process work well. He even worked out that this energy level should be about 7,600,000 electron volts. Soon after, a research team led by William A. Fowler proved that this energy level really did exist, and their results closely matched Hoyle's guess. But in 2010, a historian of science named Helge Krag argued something different. He argued that Hoyle had not really used anthropic reasoning when he made his guess in 1953. Krag said that anthropic reasoning, the idea that the universe seems to be fine-tuned for life, did not become widely talked about until 1980. He claimed that Hoyle and other scientists only made the link between carbon and life after the resonance had already been found. Krag called this idea an anthropic myth. Another interesting debate in cosmology is about the theory of cosmic inflation. This theory explains how the universe grew extremely fast in its earliest moments. A scientist named Don N. Page criticized this theory by pointing to a big problem. For time to move forward, the universe had to begin with an incredibly low level of disorder or entropy. But this starting point seems to be very unlikely. This makes the whole inflation theory doubtful. However, the scientist Paul Davies disagreed. He said that an inflationary version of the anthropic principle fixes this problem. Davies agreed that the early universe had to be very orderly, basically a tiny, neat patch of space that later grew into the universe we see now. He believed that this actually made the inflation theory stronger. It did so since it removed the need for extra guesses about how the universe began. These were guesses that other Big Bang theories still need. Another big idea in modern physics comes from string theory. This theory says that instead of just one universe, there may be a huge number of possible universes. These different universes, called vacua or backgrounds, make up what scientists call the multiverse. They also call it the string landscape. The scientist Leonard Susskind said that if there are countless universes, then anthropic reasoning makes sense. This is because we only exist in a universe that has the right conditions for life. If other universes do not allow life, we simply never notice them. The famous scientist Steven Weinberg saw the anthropic principle as an important shift in scientific thinking. He thought that cosmologists who do not believe in a divine creator could use the principle. They could use it to explain why the basic constants of nature seem to be perfectly suited for life. He called it a turning point in modern science. He said this because it could explain the exact values of these constants without assuming that a higher power had carefully adjusted them. But not everyone agreed. Scientists like David Gross, Lubos Motyl, Peter Woit, and Lee Smolin argued that this way of thinking does not really predict anything useful. Meanwhile, researchers such as Max Tegmark, Mario Livio, and Martin Rees noted something. Many accepted scientific theories cannot be fully tested yet, but they are still seen as valid. Between the years 2000 and 2002, a scientist named Jürgen Schmidhuber gave another view. He pointed to Ray Solomonoff's theory of universal inductive inference. This theory gives a logical way to judge scientific theories based on limited observations. Schmidhuber argued that this method already gives scientists the best possible way to decide which theories are the most reliable. It does so even if they cannot test everything directly. Two researchers, Jiawei Zhang and Samuel L. Braunstein, studied the idea that life's existence in the universe depends on certain basic physical constants. Their results suggested something. If scientists do not fully understand these constants, they might wrongly think that the universe was purposely designed for life. This challenges the idea that our universe is uniquely special. This is because if different constants could also allow life in other universes, then ours may not be as rare as it seems. String theory is a complicated but very interesting idea in physics. It says that the tiniest building blocks of the universe are not just tiny dots like traditional particles. Instead, they are tiny vibrating strings. These strings move through space and interact with one another, and the way that they vibrate decides the properties of the particles that we see, such as their mass and charge. If you look at a string from far away, it acts like a normal particle, but up close it is really a tiny loop or a strand. One of the most important predictions of string theory is that one of these vibrations matches the graviton. This is a particle that is believed to carry the force of gravity. Because of this, string theory is seen as a possible explanation for quantum gravity. Quantum gravity tries to join gravity with the strange and powerful rules of quantum mechanics. Scientists are interested in string theory because it offers a possible way to answer some of the deepest mysteries in physics. Over the years, it has helped researchers make progress in understanding black holes, the early universe, and even the forces inside atoms. It has also influenced math research in surprising ways. But the biggest reason that string theory is so exciting is that it could be a theory of everything. This would be a single framework that explains all of the basic forces of nature. These forces include gravity, electromagnetism, and the nuclear forces that hold atoms together. However, even after many decades of research, scientists are still trying to find out something. They want to know whether string theory truly describes the real universe, or if it allows for too many choices to make clear predictions. String theory first appeared in the late 1960s as an attempt to explain the strong nuclear force. This force holds the atomic nuclei together. But when another theory, quantum chromodynamics, was found to be a better explanation, scientists set string theory aside. However, they later saw that string theory had surprising features. These features made it a strong candidate for explaining gravity at the quantum level. The first version of string theory was called bosonic string theory. It only included one type of particle known as bosons. Later, the theory grew into what is now called superstring theory. This brought in the idea of supersymmetry. This idea suggests a deep link between bosons and another type of particle known as fermions. Over time, physicists found 5 different versions of superstring theory, but in the mid-1990s they found strong proof that all 5 were actually different views of one larger theory. This theory was called M theory. It needs a universe with 11 dimensions instead of the usual 3 dimensions of space and 1 of time. In the late 1990s, scientists also found an important connection. This was called the anti-de Sitter conformal field theory, or ADS, CFT correspondence. This discovery linked string theory to another major area of physics, quantum field theory. It showed that the two could give new insights into each other. One of the biggest problems with string theory is that scientists still do not have a full and clear definition of the whole theory in every case. Another problem is that string theory predicts a huge number of possible universes. This makes it hard to know which version, if any, matches our own. These troubles have led some physicists to ask whether string theory is truly the right path, or if too much work is being put into an idea that may never be testable. In the 20th century, physicists built 2 major theories that explain the universe. The first one was Albert Einstein's general theory of relativity. It describes gravity and the structure of space and time on a large scale. This includes planets, stars, and galaxies. The second one was quantum mechanics. It explains the strange behavior of tiny particles like electrons and photons. By the late 1970s, these 2 theories were enough to explain almost everything seen in nature. This ranged from the smallest particles to the growth of the whole universe. However, despite their success, there was a huge problem. These 2 theories do not work well together. General relativity is based on classical physics, while quantum mechanics follows very different rules. To fully understand the universe, scientists need a quantum theory of gravity, but the attempts to join the 2 have faced big problems. String theory is one of the most hopeful ideas for solving this puzzle, but it is still unfinished. String theory starts with an exciting idea. What if the tiny particles that we think of as points in space are actually tiny vibrating strings? Instead of treating them as dots with no size, string theory imagines them as very small, one-dimensional threads. These threads move and shake in space. These strings can be either open like a short line or closed, forming a tiny loop. The way that they vibrate decides their properties like their mass, their charge, and how they interact with other particles. From a distance, these vibrating strings look just like the basic particles that physicists already study. They fit into the existing models of physics. But when they are observed on extremely small scales, smaller than anything we can measure right now, they act in a way that could explain the mysteries of the universe. One of the most exciting possibilities is that one of these vibrations matches the graviton. This is a possible particle that is thought to carry the force of gravity. If this is true, it would mean that string theory naturally includes gravity. This is something that no other main theory of physics has managed to do. Over the past several decades, physicists working on string theory have made a remarkable finding. The different versions of the theory, which at first seem to be separate, are actually connected. They are connected through mathematical links known as dualities. These dualities show that what looks like one type of theory from one view may actually be another type when seen differently. This finding led to the idea that all of the consistent versions of string theory might be part of a bigger, united framework. This framework is known as M-theory. However, no one fully understands what M-theory really is yet. It is still unfinished. String theory has also given surprising insights into black holes and the nature of gravity. For decades, physicists have struggled with strange puzzles that appear when trying to apply quantum mechanics to black holes. In the late 1990s, a breakthrough came with the discovery of the anti-de Sitter conformal field theory correspondence. This is often called the ADS CFT correspondence. This discovery linked string theory to other well-known areas of physics, helping scientists study black holes in new ways. The ADS CFT has even found uses in areas outside of gravity. These include nuclear physics and condensed matter physics, which study the behavior of particles in extreme conditions. Because string theory tries to include all basic forces of nature, including gravity, it has been suggested as a possible theory of everything. Many physicists hope that if string theory can be fully worked out, it will give a complete explanation of the universe. It would explain why particles have the masses and charges that they do, and how dark matter fits in, and even how the early universe grew. However, there are still big problems. Physicists do not yet know whether string theory truly describes our universe, or whether it allows for many different possible universes. One of the biggest problems in string theory is that it is not fully understood in all cases. The easiest way to study how strings behave is through a math method called perturbation theory. This method works by making small guesses. However, this method does not show everything about string theory, and physicists do not yet know how to define the theory in its full form without these guesses. Another unsolved puzzle is how string theory sets the vacuum state, the basic state of the universe. Without this knowledge, it is unclear how much freedom the theory has in shaping the universe that we see today. Some critics say that these unanswered questions make string theory too uncertain. Others believe that it is still worth studying. To see where string theory fits into modern physics, it helps to look at quantum field theory. This is the base of particle physics. Quantum field theory is the math framework used to describe tiny particles. It treats them as ripples in the underlying fields. In this theory, scientists work out the chances of particle interactions by using a method called perturbation theory. This method was created in the early 20th century by physicists like Richard Feynman. A key tool in this method is the Feynman diagrams. These are drawings that help to show how particles interact. String theory builds on these ideas, but makes a bold change. Instead of picturing particles as points moving through space, it describes them as tiny strings. In a traditional quantum field theory, a Feynman diagram shows a particle's path as a one-dimensional line. In string theory, this line is replaced by a two-dimensional surface. This surface shows the path of a vibrating string. This change alters the math and could explain things that quantum field theory struggles with, such as gravity. However, one of the major problems remains. String theory does not yet have a full definition that is beyond perturbation theory. This makes it hard to answer all the questions that physicists want to explore. One of the most important parts of string theory is the scale at which it works. The length of a basic string is thought to be about 1/10,000,000th of a trillionth of a trillionth of a meter. This is the Planck length. This is so incredibly small that at the scales we can study in experiments, these strings would look like tiny points. Only at the Planck scale do the effects of quantum gravity become important. This makes string theory a possible explanation for how gravity works at the smallest levels. At first, string theory was developed as bosonic string theory. This theory focused only on bosons, the particles that carry forces like photons in electromagnetism. However, this version had serious problems, so scientists expanded the idea into superstring theory. This theory includes both bosons and fermions, the particles that make up matter like electrons and quarks. Superstring theory also uses supersymmetry. This is an idea that suggests that every force-carrying boson has a matching matter particle, a fermion, and the other way around. There are 5 main versions of superstring theory. These are type I, type Ia, type IIb, and 2 types of heterotic string theory. Each version allows for different types of strings, and at lower energy levels they produce different physical properties. For example, type I string theory includes both open strings which have loose ends and closed strings which form loops. The other versions focus only on the closed strings. In our daily experience, we know the 3 dimensions that describe space. These are height, width, and length. These 3 dimensions help us to understand the shape and size of the things around us. However, Albert Einstein's groundbreaking theory of general relativity introduced a shocking idea. Time is not separate from space, but is actually a 4th dimension. Together they form what scientists call space-time, a 4-dimensional fabric that shapes the very structure of the universe. In this model, gravity is not simply a force pulling objects toward each other, as Isaac Newton once thought. Instead, gravity comes from the way that space-time bends and curves around heavy objects like planets and stars. Even though this 4-dimensional space-time model explains a lot about how the universe works, scientists often explore theories that involve even more dimensions. Sometimes adding extra dimensions makes difficult math problems easier to solve. This helps physicists to understand the universe better. In fact, certain scientific areas like condensed matter physics can be described using theories with just 2 or 3 dimensions. Condensed matter physics studies how materials behave. But what if the universe really has more than 4 dimensions and we just have not seen them yet? Some theories suggest that extra dimensions might exist hidden in ways that we cannot easily notice. One of the most fascinating ideas in modern physics is string theory. This theory suggests that at the deepest level, everything in the universe is made up of tiny vibrating strings. It suggests this instead of point-like particles. However, for string theory to make sense mathematically, it needs extra dimensions beyond the 4 that we know. The different versions of string theory predict different numbers of dimensions. Bosonic string theory suggests that spacetime has 26 dimensions. Superstring theory requires 10 dimensions, and an advanced version called M theory suggests that there are 11 dimensions. But if these extra dimensions are real, then why do we not see them? One of the possible answers is in a concept called compactification. This idea says that the extra dimensions are curled up so tightly that they are too small for us to notice. Imagine looking at a garden hose from far away. It might seem like a simple one-dimensional line, but if you get closer, you will see that it actually has a second dimension, its round width. An ant crawling on the hose would experience both dimensions, but from a distance they seem to be hidden. In the same way, if extra dimensions exist, they might be curled into shapes that are so tiny that we do not see them in daily life. To correctly describe the universe by using string theory, these extra dimensions must be curled up in a very specific way. Scientists believe that they must take the shape of a special 6-dimensional structure. This structure is called a Calabi-Yau manifold. This structure is named after the mathematicians Eugenio Calabi and Xingtung Yau, who studied its properties. Only certain types of Calabi-Yau shapes would allow string theory to properly describe the basic forces of nature. These forces include electromagnetism, the weak and strong nuclear forces, and gravity. Another fascinating way to think about extra dimensions is through something called the brain world idea. In this picture, our entire universe is really a 4-dimensional brain that is floating inside a higher dimensional space. Think of a soap bubble floating in the air. The surface of the bubble is like our universe. The air around it represents the extra dimensions that we cannot directly see. According to this idea, particles and forces like electromagnetism are trapped inside our four-dimensional universe, but gravity might be able to spread into the extra dimensions. This could explain why gravity is so much weaker than the other basic forces. It might be leaking into the hidden dimensions. String theory also brings in the idea of a duality. This means that theories that look very different might actually be the two sides of the same coin. One type of duality, called S-duality, says something interesting. A group of particles that strongly interact in one theory can be described as weakly interacting in another. Strongly interacting particles frequently collide and combine. Weakly interacting particles rarely collide. This means that complex physical interactions might have simpler explanations from another point of view. For example, type-wine string theory is mathematically equal to another theory called the SO heterotic string theory through an S-duality. Another type of duality, called T-duality, deals with how strings behave in the curled-up extra dimensions. It says that if a string moves around a circular dimension of a certain size, it can act exactly like a string moving around a much smaller circle. This means that a universe with large extra dimensions might look the same as one with very small extra dimensions. Type II and type IIb. String theory, for instance, are actually equal through a T-duality, even though they seem to be different at first. Duality is a powerful idea that shows up not just in string theory, but in other areas of physics too. A well-known example is the ADS, CFT correspondence, which links string theory to quantum field theory. This surprising link has given new insights into how particles and forces behave at the smallest levels. In simple words, when two theories are related by a duality, it means something. If you change one theory in a certain way, it will end up looking just like the other. Even though they seem different at first glance, they are really describing the same reality using different types of math. Another important idea in string theory is the idea of branes. A brane, which is short for membrane, is a multidimensional object that stretches the idea of a point particle into higher dimensions. A zero-dimensional brane is just a point. A one-dimensional brane is a string, and higher dimensional branes are called p-branes, where p stands for the number of space dimensions. These branes move through space-time according to the rules of quantum mechanics, and they can have features like mass and charge. They also interact with the basic fields, just like how charged particles interact with electric and magnetic fields. A special type of brane called a D-brane plays an important role in string theory. Open strings, the strings with two loose ends, must have their ends attached to a D-brane. The D stands for Dirichlet boundary conditions, a math rule that controls how the strings behave. D-branes have been key in discoveries like the ADS, CFT correspondence. This has helped to explain many puzzles in quantum physics. The universe is full of mysteries, and one of the biggest is dark energy. This strange force is what makes the universe expand faster and faster. Scientists think that dark energy makes up about 68% of everything in the universe. In comparison, dark matter, another hidden substance, makes up about 26%. All of normal matter, the stars, planets, and everything we can see, only adds up to about 5%. Other forms of energy, such as light particles and neutrinos, are so small in comparison that they hardly count. Even though dark energy has an extremely low heaviness, it still controls the universe. Its heaviness is about 7 times 10 to the power of negative 30 grams in every cubic centimeter. This is because, unlike matter, which gathers together into galaxies and stars, dark energy is spread out evenly across space. No matter where you go in the universe, dark energy is always there, filling every part of the cosmos. Scientists first thought that dark energy might exist when they studied faraway exploding stars. These were known as type Ia supernovae. These supernovae act like cosmic measuring sticks, because they shine with the same brightness. They shine the same no matter how far away they are. By watching how their light stretches as it travels through space, a process called redshift, scientists can figure out how quickly they are moving away. What they found was shocking. Instead of slowing down, the universe was expanding faster and faster. This was the opposite of what scientists expected. Before this discovery, most of them believed that gravity from all the matter in the universe would slowly slow down the expansion. This is much like how a thrown ball slows before falling back to the ground. But the data showed that some unknown force was pushing the universe apart. That force was later called dark energy. There are several ideas about what dark energy could be. One of the main ideas is called the cosmological constant. This says that dark energy is a constant, unchanging force that fills space. It is sometimes described as the energy of empty space or a vacuum energy. Another idea is that dark energy comes from scalar fields. This is a type of energy that changes over time and space. These fields could act differently in different parts of the universe. This would make dark energy more changeable. Some versions of this idea include quintessence and the moduli fields. Other theories suggest that dark energy could interact with gravity in ways that we do not yet understand. One idea, called cosmological coupling, suggests that dark energy and gravity might be linked in some unknown way. Another idea interacting dark energy suggests that dark energy might be affected by other unseen forces in the universe. The idea of a strange energy filling space actually goes back to Albert Einstein. In the early 20th century, Einstein added something called the cosmological constant lambda into his equations. This was his theory of general relativity. At the time, scientists thought that the universe was unmoving, neither expanding nor shrinking. To make his equations fit this view, Einstein added the cosmological constant. This constant acted as a force pushing against gravity, stopping the universe from collapsing in on itself. But in 1929, the astronomer Edwin Hubble discovered that the universe was not still at all. It was actually expanding. This made Einstein see that his first idea was wrong. He later called the cosmological constant his greatest mistake. Ironically, many decades later, scientists found that a repelling force, what we now call dark energy, was indeed pushing the universe apart. This means that Einstein's idea may not have been a mistake after all. In 1980, the physicists Alan Guth and Alexei Starobinsky suggested a groundbreaking idea called cosmic inflation. This idea says that just after the Big Bang, the universe went through a very short but extremely fast growth. It was expanding at an unbelievable speed. This inflation period shaped the structure of the universe, and it explains why galaxies are spread out the way that they are today. Inflation looks a lot like dark energy, since both involve a very fast expansion of space. But the energy behind inflation was much stronger than the dark energy we see today. Scientists are still trying to understand if these two forces are connected or completely separate. By the 1980s, scientists had built models of the universe that relied heavily on cold dark matter. This is a form of dark matter that moves slowly compared to the speed of light. These models did a good job of explaining how galaxies were formed, but they had some problems. For example, they predicted a slower Hubble constant, the rate of the universe's expansion, than what astronomers actually observed. The situation changed in 1992 when NASA's COBE spacecraft found small irregularities. These were in the cosmic microwave background, the faint glow left over from the Big Bang. This discovery pushed scientists to rethink their models. A major turning point came in 1998 when astronomers studying faraway supernovae found clear proof. They found proof that the universe's expansion was speeding up, not slowing down. This was the first direct proof that dark energy was real. More discoveries followed. In the early 2000s, experiments like Boomerang and Maxima studied the cosmic microwave background. They found that the universe's total energy density was very close to what is known as the critical density. This is the exact amount needed to make the universe flat on large scales. But when scientists measured the amount of matter in the universe, they found that it was only about 30% of this critical density. The missing energy was explained by dark energy. Further proof came from the 2-degree field galaxy redshift survey in 2001. This survey measured the spread of galaxies and showed that dark energy was needed to explain the results. Then, from 2003 to 2010, NASA's WMAP satellite gave even more exact measurements of the cosmic microwave background. This strengthened the lambda CDM model as the best explanation for how the universe is built and how it changes. The name dark energy was first used in 1998 by the physicist Michael S. Turner. This followed the earlier term of dark matter, which had been introduced by Fritz Zwicky in the 1930s. Despite all of these discoveries, dark energy remains one of the biggest puzzles in modern physics. Some scientists think that it could be a basic property of space itself. Others think that it might be linked to quantum mechanics. These are the strange rules that control particles at the tiniest scales. Future experiments, including new space telescopes and large galaxy surveys, aim to find more clues about this strange force. To truly understand how the universe grows and stretches over time, scientists need to take very exact measurements. They need to measure its expansion. In the world of general relativity, researchers figure out how fast the universe is expanding. They do this by studying its shape and a key idea known as the cosmological equation of state. This equation explains how things like temperature, pressure, and the combined amounts of matter energy and vacuum energy work together in different parts of space. One of the biggest challenges in modern cosmology is working out the equation of state for dark energy. Scientists believe that dark energy plays a major role in the universe's rapid expansion, but its true nature is still a mystery. To study this, researchers include the cosmological constant in the Standard Model of Cosmology. This is also called the Friedmann-Lemaitre-Robertson-Walker model. This leads to what experts call the lambda-cold dark matter model, or the lambda CDM model. It is often called the gold standard of cosmology because it closely matches what we actually see in the universe. Since 2013, the lambda CDM model has been tested many times. It has been tested through highly exact observations, including data from the Planck spacecraft and the Supernova Legacy Survey. An early result from this survey suggested that dark energy acts almost exactly as Einstein's cosmological constant predicts. It did so with an accuracy of about 10%. More recent findings from the Hubble Space Telescope's High-Z team show that dark energy has been affecting the universe for at least 9 billion years. This was long before the universe began its rapid speeding up. Yet despite these findings, dark energy remains one of the greatest mysteries in physics. It seems to be very smooth and evenly spread across space with an incredibly low density. Unlike other forms of energy or matter, it does not seem to interact with anything except gravity. Its density is astonishingly small, about 1/10,000,000th of a trillionth of a trillionth of a kilogram in every cubic meter. This makes it almost impossible to detect in laboratory experiments. Yet even though it is so faint, dark energy makes up about 68% of the universe's total energy. This is because, unlike matter which clumps together, dark energy spreads out evenly across all of space. This deeply affects the universe's expansion. One of the main explanations for dark energy connects it to something called vacuum energy. This refers to the tiny changes of particles and antiparticles that constantly appear and disappear in empty space. This follows Heisenberg's uncertainty principle. According to Einstein's theory of relativity, this vacuum energy should have a gravitational effect. This means that it adds to the cosmological constant, This in turn is believed to be one of the main reasons that the universe's expansion is speeding up. But there is a huge problem. When physicists use quantum field theory to predict how much vacuum energy should exist, they get a number that is far greater than what is actually seen. This massive gap between theory and reality remains one of the greatest unsolved problems in modern physics. Regardless of what dark energy really is, for it to cause the faster spreading of the universe, it must have a very strong pulling force. This force would be in the opposite direction and is called a negative pressure. In general relativity, pressure acts in a similar way to mass when it comes to its pull by gravity. Both pressure and mass are part of something called the stress-energy tensor. This decides how matter and energy affect gravity. In the case of dark energy, this opposite pressure works against gravity. It makes space spread out faster and faster. If the universe were shrinking instead, this same pressure would slow down its squeezing. This effect is sometimes called gravitational pushing away. This is because it seems to force everything apart, working against the normal pull of gravity. When we break down the universe into its main parts, we see that everything we know fits into three wide groups. These are matter, radiation, and dark energy. Matter includes everything that has mass, from stars and planets to tiny dust grains. As the universe spreads, the energy of matter thins out in proportion to the cube of the spreading factor. Think of a box filled with particles. If the box becomes twice as large, the energy of the particles inside does not just get cut in half. It goes down by a factor of 8 because the space inside grows in 3 directions. Radiation, which includes light and heat, acts a little differently. As space spreads, the energy of radiation drops even faster than that of matter. This is because, apart from spreading over a bigger space, the waves of light and radiation also get stretched. This stretching, called a redshift, makes the radiation lose energy quicker than matter does. Dark energy, however, acts in a completely different way. Unlike matter and radiation, its energy does not thin out as the universe grows. Instead, it stays the same no matter how large the universe becomes. In simple terms, while matter gets thinner as space grows, dark energy remains steady. It fills the emptiness evenly and drives the universe's faster spreading. Scientists have gathered many pieces of proof that point to the existence of dark energy. This is true even though it has not been directly found. Distance and redshift measurements. By studying how light from faraway objects has stretched over time, scientists discovered something. The universe has been spreading faster in recent times than it did long ago. This shows that something likely dark energy is causing this faster growth. The need for an extra energy. The universe looks to be flat in shape, meaning it does not bend inward or outward. For the universe to be flat, there must be a certain amount of total energy. Since normal matter and dark matter together are not enough, scientists believe that dark energy must be filling the gap. The patterns in cosmic structures. When astronomers study the large-scale layout of galaxies, they see patterns that hint at the role of dark energy. The way that galaxies are spread across space gives more clues about the spreading of the universe and about the strange force that is behind it. In 1998, a group of astronomers called the High Z Supernova Search Team made a shocking finding. They did so while studying a special kind of exploding star known as the type Ia supernovae. They thought they would find that the universe's spreading was slowing down due to gravity, but instead they found the opposite. It was speeding up. Just 1 year later, in 1999, another group of scientists, the Supernova Cosmology Project, reached the same surprising result. Their groundbreaking work changed our understanding of the universe, and it earned them the Nobel Prize in Physics in 2011. Since then, many more studies have confirmed this finding. Studies of the cosmic microwave background, the faint glow left over from the Big Bang, have given strong proof. Astronomers have also looked at how light bends around huge objects in space, which is called gravitational lensing, and they have looked at how galaxies are spread out. All of these findings support the idea that a strange force called dark energy is driving the faster growth of the universe. Some doubters argue that the strongest proof comes only from measuring a redshift and supernova distances. A redshift is how light stretches as objects move away. But other evidence, such as the patterns in the cosmic microwave background, also shows something. The universe is spreading faster than it would without dark energy. Supernovae are very useful for studying the universe because they act like natural measuring tools. These are often called standard candles. Scientists know exactly how bright these explosions should be. This helps them to tell how far away they are. By comparing a supernova's distance with how much its light has stretched, its redshift astronomers can measure how quickly the universe is spreading. Type Ia supernovae are especially valuable because they always explode with the same brightness. This makes them among the most trusted cosmic markers. Recent studies show that dark energy makes up about 71% of the universe. The other 29% is made of dark matter and normal matter. The leading idea that explains how galaxies, stars, and other cosmic structures were formed says that matter only makes up about 30% of the universe's total critical density. This is the amount needed for the universe to stay flat. More proof of dark energy came in 2011 from the WiggleZ Galaxy Survey. This survey studied more than 200,000 galaxies. Scientists used a new method to measure the distances to galaxies as far as 2,000 million parsecs away. Their results confirmed that the universe has been spreading faster. This gave even stronger proof for cosmic speeding up. For the universe to be as flat as it looks, there must be an extra energy filling space. All of the visible matter, both normal and dark, makes up only about 30% of what is needed. The other 70% is believed to be dark energy. Data from the Wilkinson Microwave Anisotropy Probe, which mapped the early universe, showed that dark energy makes up about 73%. Later findings from the Planck satellite updated this. They showed that dark energy makes up about 68% dark matter, about 27%, and normal matter just under 5%. Dark energy also helps to explain the strange patterns in the cosmic microwave background. When light particles called photons travel through regions of strong gravity like galaxy clusters or empty spaces, they gain or lose energy. This makes temperature changes in the background radiation and is known as the integrated Sachs-Wolfe effect. It is seen as another strong clue of dark energy. Scientists are also using a new method to study dark energy. They are measuring the Hubble constant, which describes how the universe's growth rate changes over time. They study galaxies that have grown in a steady way, treating them like cosmic clocks. By looking at their ages and their redshifts, they can estimate how fast the universe was growing at different times. Even with all of this proof, dark energy is still one of the biggest unsolved riddles in physics. Scientists agree that it plays a key role in making the universe spread faster, but they do not fully know what it is or how it works. To find the answers, some of them are rechecking Einstein's theory of gravity to see if a change is needed. Others are studying the exact traits of dark energy. Some of them are even looking at other possible reasons based on new cosmic findings. One of the simplest ideas about dark energy is that it is a basic feature of space itself. In this view, even a totally empty space holds a form of energy which is often called vacuum energy. This idea is known as the cosmological constant and is shown by the Greek letter lambda. It is the base of the lambda CDM model, which is now the most accepted idea of the universe's shape. Since Einstein's famous equation shows that energy and mass are linked, this vacuum energy should also have a gravitational effect. It should change how the universe grows. But there is a very big problem with this idea. Calculations from quantum physics suggest that the amount of vacuum energy should be unbelievably large. It should be about 120 orders of magnitude higher than what we actually see. If that were true, the universe would have spread so quickly that galaxies, stars, and planets could never have been formed. Yet here we are in a universe where galaxies and stars have been formed and changed over billions of years. Something must be cancelling out most of this energy, but not all of it. Scientists do not yet know why, which makes dark energy one of the greatest puzzles in today's physics. While many of them believe that dark energy is a constant, unchanging force, some scientists think it could be something much more active. They think it could be an energy field that changes over time. This idea is called quintessence. Unlike the cosmological constant, which stays the same everywhere, quintessence acts like an energy field. It is spread across the universe, affecting its growth in different ways at different times. It is thought to be extremely light, so that unlike normal matter, it does not gather into stars and galaxies. Some versions of this idea suggest that the universe's spreading is happening a little slower than the standard model says, but so far there is no strong proof to fully support or reject this idea. One of the biggest unanswered questions about dark energy is why it became the main influence at this particular time. This is at this point in the history of the universe. If it had taken over too early, the universe's fast expansion could have stopped galaxies from forming, and life as we know it might never have existed. Some scientists think that this is just a coincidence. Others believe that it supports a controversial idea called the anthropic principle. This is the idea that the universe must be the way it is because we are here to see it. Interestingly, some quintessence models include a built-in system called a tracker. This system naturally explains why dark energy became important at this exact time. According to these models, dark energy's behavior is linked to the amount of radiation in the early universe. This could explain why it appeared later, but with strong effects. Some extreme versions of quintessence predict even stranger situations. One of these is phantom energy, a type of dark energy that gets stronger over time instead of staying the same. If this idea is correct, the universe would not just keep on expanding. It could eventually be torn apart in a frightening event called the Big Rip. In this doomsday scenario, the force of expansion would grow so strong that it would first tear apart galaxies, then it would tear apart stars, then planets, and finally even atoms themselves. This would leave everything as nothing. Another version of quintessence, called K-essence, suggests that dark energy could be made of unusual forms of energy. These would act in ways that were never seen before. Some types of K-essence even suggest the existence of negative kinetic energy. This could have strange and unpredictable effects on the universe's growth. In recent years, astronomers have found differences in the measurements of how fast the universe is expanding. This disagreement, called the Hubble tension, suggests that the standard model of cosmology might be missing something important. Some researchers think that only certain types of quintessence models with extra interactions can explain this difference. Even though dark energy is still one of the biggest mysteries in modern physics, it is closely linked to Albert Einstein's theory of general relativity. Some scientists say that if general relativity were changed in certain ways, we might not need dark energy at all. We might not need it to explain the universe's faster expansion. Several alternative theories have been suggested, but so far none of them have been fully proven. In fact, an important discovery, the detection of gravitational waves from the event known as GW170817, has already ruled out many of these changed gravity theories. According to the astrophysicist Ethan Siegel, while new ideas about dark energy often make the news, most experts still believe that dark energy is real. The competing theories simply do not match the observations as well as the current model. Scientists estimate that the universe's expansion started speeding up about 5 billion years ago. Before that, gravity, which was mainly from dark matter and normal matter, was slowing everything down. But as the universe grew bigger, dark matter spread out and became less important. Meanwhile, dark energy stayed almost the same. Eventually, dark energy took over, causing the expansion to speed up. Every time the universe doubles in size, the amount of dark matter in a given space is cut in half, but dark energy stays almost the same. What happens next depends on the nature of dark energy. If it stays the same as the cosmological constant suggests, the universe will keep on expanding forever. The distant galaxies will move away from us faster and faster. They will eventually reach speeds greater than light itself. This does not break any laws of physics. This is because space itself is stretching rather than the galaxies moving through space. Right now, scientists estimate that the cosmological event horizon is about 16 billion light-years away. This is the distance beyond which we can never receive signals or light. If something happens within that distance, its light may still reach us far in the future, but anything beyond that distance will be lost to us forever. As galaxies get closer to this horizon, the light they send out will be stretched. It will be stretched into longer and longer wavelengths, eventually becoming invisible. To an observer in the far future, those galaxies will seem to fade away. They will fade until only our own local group of galaxies is left in an otherwise empty universe. While the idea of an endlessly expanding dark and empty universe is unsettling, some alternative theories predict more dramatic endings. If dark energy keeps on getting stronger, the Big Rip could happen, destroying everything in existence. But there are also theories suggesting that dark energy might change over time, possibly reversing its effects. In that case, the universe could stop expanding and start shrinking in a big crunch. It could eventually collapse back into a single point. This could possibly lead to another Big Bang and the birth of a new universe. Another possibility is that dark energy follows cycles. This would cause the universe to expand and shrink in an endless loop of Big Bangs and big crunches. When we think about the beginning of the universe, a question often comes to mind. What was there before anything existed? How did everything come into being from what seems like nothing? This question has puzzled scientists, philosophers, and thinkers for hundreds of years, and it touches on one of the deepest mysteries of existence. At the center of this puzzle is the idea of nothingness, a void, an emptiness. This was a space that existed long before atoms, stars, and galaxies came into being. But the story of this nothingness is far more complicated and fascinating than we might first think. This nothingness is not just an absence of matter. It is a strange state that has the potential to create everything that we know. Before diving into the puzzles around nothingness, it is important to understand what we mean by the word nothing. In our daily lives, nothing seems like an easy idea to understand. If you have an empty room, you might think that there is nothing in it. But even then, the room is filled with air, light, and the potential to hold something else. The nothing that space scientists talk about is not this simple emptiness. Instead, it is a state without any matter, any energy, or even space itself. It is a true void, a state of complete nothingness. Now, let's imagine a time before the universe was born. There were no stars, no planets, no atoms, and not even the space that we think of today. In fact, the very idea of space did not exist the way that we understand it. It was a moment before the Big Bang, a time when the rules of physics, as we know them, did not work the same way. At this point, everything that we call something was still waiting to be created. So what was this nothingness like? Was it really empty, or was something more subtle and strange happening in the void? According to modern physics, this emptiness was not as inactive as it may seem. In fact, this vacuum of nothingness may have been the birthplace of all of the matter, energy, and forces that make up our universe today. The question of how something can come from nothing is often called a paradox. If there was nothing, then how could anything come into existence? It seems to go against all of logic and common sense. But modern science, especially quantum physics, gives a surprising answer. In the world of quantum physics, nothing is not really empty. Even in a vacuum, there is a strange and mysterious activity happening. This activity is called quantum fluctuations. Quantum fluctuations are tiny, unpredictable changes in the energy of an empty space. These fluctuations are brief bursts of energy that can appear out of nothing for a moment and then disappear. While these energy bursts are extremely small and short-lived, they are real and measurable. They show that even in a true vacuum, where no particles exist, there is still a kind of activity happening on the smallest levels. We cannot see this with our eyes, but it can be detected and understood through quantum physics. Now let's bring this back to the creation of the universe. The Big Bang, which is thought to have happened about 13 billion years ago, was not an explosion in space. It was the expansion of space itself. At the very beginning, all of the energy and matter that would eventually form the universe were concentrated. They were concentrated in an extremely hot, dense point called a singularity. But how did this singularity come to be, and how did it come from nothing? Some scientists suggest that the energy changes in the quantum vacuum could have started the Big Bang. Basically, the vacuum of nothingness decided to shake things up and create particles, energy, and eventually the entire universe. This process is called quantum creation. It shows that space itself can fluctuate, and under the right conditions, these fluctuations could produce matter and energy. In this way, the rules of physics that control the behavior of particles and energy in our universe could have come from the very nothingness that existed before. This idea leads to a fascinating possibility. Maybe the whole universe, everything that we see around us from the smallest particles to the largest galaxies, was born from a quantum fluctuation. It could have been born in the vacuum of nothingness. In this view, the creation of the universe was not a single event. It was the result of ongoing fluctuations in the fabric of space and time. So, if the universe came from nothing, then how do the rules of physics fit in? How can the universe follow consistent rules if it was created from a void, from a state where no rules existed? This question challenges our understanding of the universe, but it is here that the beauty of science becomes clear. One important idea to understand is that the rules of physics themselves are not random. They come from the basic properties of the universe. When we talk about the rules of physics, we mean the principles that control how matter and energy behave. These rules include gravity, the way subatomic particles interact, and the principles of heat and energy. But where did these rules come from? How did they come out of nothingness? According to current scientific ideas, the rules of physics might not have been the same as they are today, not at the time of the Big Bang. In the very early moments of the universe, shortly after the Big Bang, the rules of physics may have been very different. For example, it is thought that the universe went through a period of very fast expansion called inflation. During this time, space itself grew enormously, and the main forces of the universe may not have been separate. These forces are gravity, electricity, and magnetism, and the strong and weak nuclear forces. In the very high energy environment of the early universe, these forces might have been combined into a single superforce. This superforce slowly split apart as the universe cooled. The idea that the rules of physics could change over time is amazing, but it is supported by observations and mathematical models made by scientists. As the universe cooled and expanded, the conditions changed, and the forces that control matter began to take their present form. It is as if the universe started with very simple general rules. These rules slowly became the complex set of rules that we see today. In this way, the universe could have grown from the simplest beginning, a quantum fluctuation in the vacuum, into the highly structured and orderly system that we observe. The rules of physics that we follow today were not imposed from outside the universe. Instead, they are built into the very fabric of space and time. They came naturally from the conditions that appeared after the Big Bang. The quantum vacuum, which is often called empty space, is not as empty as it seems. It is actually full of potential. At the most basic level, space is filled with quantum fields that stretch across the entire universe. These fields are the building blocks of matter and energy, and they are responsible for creating particles, spreading forces, and even for the existence of space and time itself. Even when there is no matter or energy, these quantum fields are still active. They interact with each other, fluctuating with energy even without any visible particles. This activity is what causes the strange effects of quantum mechanics. Effects such as particle-antiparticle pairs that appear and vanish instantly. The idea of a quantum vacuum also challenges our usual understanding of empty space. In regular physics, empty space was thought to be a void, a total absence of anything. But in the quantum world, empty space is far from empty. It is a lively, always changing field of energy and possibility. In a way, the quantum vacuum is the source of all creation. It holds the potential for all of the particles, forces, and structures that make up our universe. The vacuum is not just a quiet emptiness. It is a place where creation can begin, where anything could possibly come from, the changes in energy and the interactions of quantum fields. In astronomy, dark matter is a strange and invisible type of matter that we cannot see. We cannot see it because it does not interact with light or any other kind of radiation. We know that it is there because of the unusual effects it has on gravity. These effects cannot be fully explained by the known laws of physics unless there is more matter than we can actually see. These strange effects show up when we look at things like how galaxies form and change over time, and how light bends around very large objects called gravitational lensing, and even the way that galaxies move within groups. We also notice its effect in the structure of the universe and in the leftover radiation from the Big Bang. This radiation is called the cosmic microwave background. In the most widely accepted model of the universe, called the lambda CDM model, the total mass and energy of the universe is made up of 5% normal matter. This is the kind we see around us, and 26.8% dark matter, and 68.2% dark energy. This means that dark matter makes up about 85% of the total mass. Dark matter and dark energy together make up about 95% of the universe's total energy. We do not know exactly what dark matter is, but it does not seem to interact with normal matter or light, except through gravity. This makes it almost impossible to detect with current technology. The main idea is that dark matter might be made of tiny unknown particles. Particles like weakly interacting massive particles or axions. Another possibility is that dark matter could be made of ancient black holes from the early universe. Dark matter can be grouped in different ways depending on how fast its particles move. These groups are cold, warm, or hot. Most scientists think that dark matter is cold. This means its particles move slowly, which lets them gather together and form structures over time. While most astrophysicists believe that dark matter exists, some of them still question the idea. A small group of scientists were puzzled by certain observations that normal dark matter cannot fully explain. They suggest that maybe the laws of gravity need to be changed. They have proposed alternative ideas like modified Newtonian dynamics or new types of gravity, but none of these ideas can perfectly explain all of the evidence that we have found so far. This suggests that even if gravity needs some changes, dark matter still seems to be an important part of the puzzle. The idea of dark matter has a long and fascinating history. It is full of interesting discoveries and ideas that help to build our current understanding of the universe. The story begins with the work of some of the brightest minds in science, starting in the late 19th century. In 1884, William Thomson, who was better known as Lord Kelvin, made some interesting observations. He talked about the possible number of stars around our sun. In a book based on a lecture series he had gave in Baltimore, Kelvin was trying to estimate how many stars were near the Sun. He did this by studying how the stars moved around our solar system. By using this information, he wondered what would happen if there were 1 billion stars within a distance of 1 kiloparsec from the Sun. At this distance, the stars would seem to move in ways that were hard to explain. This idea led to further thinking about invisible matter in space. Lord Kelvin also estimated the Sun's age to be between 20 and 100 million years. This was later shown to be wrong, but his curiosity about the stars and how they moved helped to start the early ideas about dark matter. A couple of decades later, in 1906, the French mathematician Henri Poincaré introduced the term dark matter. He called it matière obscure. While talking about Lord Kelvin's work, Poincaré suggested that there might be a hidden mass in the universe, but he also thought that this hidden matter would be less than the visible matter we can see. Although his ideas were far from correct, Poincaré's mention of dark matter brought the idea into scientific discussion. In the 1920s, dark matter continued to interest astronomers. In 1922, the Dutch astronomer Jacobus Kapteyn became one of the first to use the speeds of stars to suggest that dark matter might exist. He noticed that the way stars moved in space could be affected by unseen forces. This hinted at the presence of invisible matter. Then in 1930, the Swedish astronomer Knut Lundmark expanded on the idea. He realized that the universe must have much more mass than we could observe with our telescopes. This discovery was important because it showed that the visible universe might not be the full picture. In 1932, another Dutch scientist, Jan Oort, joined the discussion. He suggested that dark matter might exist near our galaxy. He studied the movements of stars close to our galaxy, and he concluded that there must be more mass in the galaxy than what we could see. However, he later realized that his measurements were not completely accurate, and more research was needed to understand the true nature of this unseen mass. Then in 1933, the Swiss astrophysicist Fritz Zwicky made a major breakthrough. He did this while studying groups of galaxies at the California Institute of Technology. Zwicky was studying the Coma cluster, a large group of galaxies, and noticed something unusual. The galaxies in the cluster were moving much faster than was expected based on the visible mass. This led him to suggest the presence of a huge amount of invisible mass. He called it Dunkel materia or dark matter. Zwicky estimated that the Coma cluster had around 400 times more mass than could be seen. This was based on how the galaxies were moving. He thought that this unseen mass was responsible for the gravitational force that kept the galaxies in the cluster together. Although Zwicky's estimates were wrong by a large amount, mainly because of outdated values, he was one of the first to correctly identify something. The universe must contain an unseen mass that pulls things with gravity. Zwicky, however, had a different idea about dark matter than we do today. He thought that dark matter was just ordinary matter that did not give off light. He did not think it was something completely different like the mysterious dark matter we think of today. Still, his work was an important step toward discovering dark matter. Over time, more evidence for the existence of dark matter began to appear. One of the key pieces of this evidence came from studying how galaxies rotate. In 1939, H.W. Babcock studied the rotation of the Andromeda Galaxy. This is the closest spiral galaxy to us. He found that the stars on the outer edges of the galaxy were moving much faster than was expected. This suggested that there was much more mass in the galaxy than could be seen by just looking at its visible stars. At first, Babcock thought that the strange rotation could be caused by light being absorbed inside the galaxy, or that the outer parts of the galaxy worked differently. But his observations were an early clue that something invisible was affecting the galaxy's rotation. The next year, in 1940, Jan Oort made another important discovery. He studied a galaxy called NGC 3115, and he found a large invisible halo of mass around it. This was another sign that galaxies might contain hidden matter. This matter would be beyond what we could see with the tools we had at the time. The idea of dark matter really began to catch on in the 1970s. Different scientific discoveries came together to suggest that galaxies might be surrounded by huge invisible halos of matter. In 1974, two separate research groups came to the same conclusion independently. One was from Princeton, New Jersey, led by Jeremiah P. Ostriker, P. James E. Peebles, and Amos Yahill. The other was from Tartu, Estonia, led by Jan Einasto, Ants Karsik, and N. Saar. This made the idea stronger. One of the important observations that pointed to the existence of these invisible galactic halos was the way that galaxies rotate. Both optical and radio astronomy played a big role in these findings. Vera Rubin and Kent Ford, by using a new spectrograph, made more accurate measurements. They measured the speeds of edge-on spiral galaxies. This showed surprising results in the rotation curves. At the same time, radio astronomers used advanced radio telescopes to study the 21-centimeter line of atomic hydrogen in nearby galaxies. Unlike starlight, which can only be seen from the central parts of galaxies, hydrogen gas extends much farther out. This allowed astronomers to observe the rotation patterns at much greater distances. This gave them a better picture of the total mass in a galaxy. An early study of the Andromeda Galaxy used large telescopes. These included the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish. This study showed that the hydrogen rotation curve did not behave as expected based on Kepler's laws. These laws describe how objects should move around a center of gravity. As technology improved, more sensitive equipment allowed for even further measurements. In 1975, Roberts and Whitehurst pushed the limits. They measured the rotation speed of Andromeda all the way out to 30 kiloparsecs. Their findings showed that the galaxy's rotation curve stayed flat, even at great distances. This was important because it suggested that there was much more mass out there, more mass than what we could see with regular telescopes. Their charts combined optical data with new hydrogen data. This clearly showed the surprising flatness of the outer galaxy's rotation curve. The solid curve in the graph represented the optical data from the stars. The other curve showed the total mass, which kept on increasing even in the galaxy's outermost regions. At the same time, scientists were developing even more advanced ways to study galaxies. By using interferometric arrays, multiple radio telescopes working together, researchers mapped the hydrogen rotation curves of 5 spiral galaxies. These researchers were Rogstad and Shostak in 1972. They found that all of these galaxies had flat rotation curves as well. This suggested that the mass in the outer parts of the galaxies was much higher than what could be explained by visible stars and light. By the late 1970s, it was widely accepted that dark matter halos likely existed around galaxies, and this became one of the biggest mysteries in astronomy. In the 1980s and 90s, many observations began to suggest that dark matter was real. One important study was done by Persic, Salucci, and Stell in 1996. It looked closely at 967 spiral galaxies, and it found strong evidence of dark matter's existence. Other supporting evidence included strange behaviors like gravitational lensing. This is where galaxy groups bend light from objects behind them. Other evidence included the spread of hot gas in galaxies and groups, and the tiny temperature differences called anisotropies in the cosmic microwave background. This is the afterglow of the Big Bang. Today, most scientists agree that dark matter is made of particles we have not discovered yet, and these particles are unlike anything we know. The search to find this mysterious particle has become one of the biggest quests in particle physics. Many researchers are using different methods and experiments to try to find the truth. In simple terms, when scientists talk about matter in the universe, they mean something specific. Anything that adds to the overall energy, and its density changes in a certain way as the universe expands. Specifically, it decreases as the cube of the expansion. This means that the further the universe stretches, the thinner the matter becomes. This is different from radiation, which decreases even faster. Its energy gets weaker as the universe grows following the inverse fourth power of the expansion. On the other hand, the cosmological constant acts differently. It stays the same no matter how much the universe stretches. This means that its energy density remains constant. This difference in how matter radiation and the cosmological constant act is due to a phenomenon called radiation redshift. When the universe expands, if the observable universe's size doubles, the scale factor of expansion also doubles. As a result, the energy of things like the cosmic microwave background radiation gets weaker. This is the afterglow from the Big Bang. It gets weaker because each photon has to stretch out over a larger area, reducing its energy. The same happens to ultra-relativistic particles like early neutrinos. They lose energy in a similar way. However, the cosmological constant, being a property of space itself, does not change no matter how much the universe grows. As for dark matter, this term usually refers to the parts of the universe we cannot see, but they still have mass and follow similar rules to regular matter. More specifically, dark matter often means a particular kind of invisible matter, one that is not made up of the usual particles we know, excluding something called missing baryons. Depending on the situation, the meaning of dark matter can change. The arms of spiral galaxies rotate around their center, and as you move outward from the center, the visible mass of the galaxy becomes lower. If all of a galaxy's mass were visible, it would behave like a simple system. A system where most of the mass is at the center and objects orbit it, like planets orbiting the Sun. Based on Kepler's third law, we would expect the speeds of objects to slow down. They would slow down the farther they are from the center. This is just like how planets move slower the farther they are from the Sun. But that is not what we see in galaxies. Instead, the rotation speeds of stars and gas stay the same or even increase. They do so the farther out they are from the center. To explain this strange observation, it seems clear that the mass distribution in spiral galaxies is different. It is different from the solar system. Specifically, there may be a large amount of invisible non-light-giving matter on the edges of the galaxy. This is what we call dark matter. In bound systems like galaxies, the stars are also governed by a rule called the virial theorem. This rule helps to explain how masses spread out in a system based on the speeds of the stars. When astronomers look at how fast stars are moving in systems like elliptical galaxies or dense star clusters, they can use this theorem. They can use it to figure out how the masses spread out. However, in many cases, the measured speeds do not match what we would expect based on the amount of visible mass. This is true even when we consider complex star orbits. Much like with the rotation curves of galaxies, the most logical explanation for this mismatch is that there is more invisible matter involved. Again, dark matter. Galaxy clusters are key to studying dark matter. This is because we can measure their mass in 3 different ways. By looking at the range of speeds at which the galaxies in the cluster move, by studying the X-rays from the hot gas inside the cluster, and by analyzing these X-rays to figure out the temperature and density of the gas. By using the balance between gravity and pressure, we can calculate the total mass of the cluster. Through gravitational lensing, where the mass of a group bends light from objects farther away, we can measure the group's mass. We can do this without needing to directly watch the movement of the galaxies. All 3 of these methods point to the same conclusion. Dark matter makes up about 5 times the mass of all the visible matter in these groups. One of the interesting results of Einstein's theory of general relativity is a phenomenon called gravitational lensing. This happens when large objects like galaxies or groups of galaxies sit between a light source and the observer. These large objects act like a lens bending the light that passes through them. This makes the light from the source appear to be distorted. The important thing to know is that gravitational lensing only needs the presence of mass. It does not matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, think of a group of galaxies lying between a very far away object like a quasar and us. In this case, the galaxies in the group will bend the light from the quasar, making it look different. When we talk about strong lensing, we mean the dramatic way that light from background galaxies can be bent. It can be bent into arc shapes as it passes through a large object's gravitational field. This has been seen around many faraway galaxy groups, including one known as Abell 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy group that is causing the bending. In the weak lensing case, the bending is much less noticeable, and the galaxies do not turn into arcs. Instead, we see tiny distortions in the shapes of the galaxies. By looking at these small changes, scientists can learn about how dark matter is spread out in the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and normal matter are types of matter, they behave very differently. Early in the universe, normal matter was charged and interacted strongly with light, which caused it to scatter. Dark matter, on the other hand, does not interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background through its gravitational pull, especially on large scales. It also affects the movement and density of normal matter. Because of these differences, normal matter and dark matter evolve in separate ways, and they leave clear signs on the CMB. The CMB is very close to being a perfect black body. This means it gives off a smooth, even temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped across the sky. When scientists break down this map into a graph called the angular power spectrum, they see a series of peaks. These peaks are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology. And by comparing these positions to theoretical models, we can learn more about the universe's makeup. The first discovery of the CMB's anisotropies came in 1992 by the COBE satellite, but the resolution was not high enough to see the detailed peaks. In 2000, the Boomerang experiment, which used a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more precisely. Their findings supported the lambda CDM model of cosmology. Structure formation is the process that began shortly after the Big Bang. It began when small irregularities in the universe's density caused matter to collapse and form stars, galaxies, and groups of galaxies. Before this period, the universe was uniform with no significant differences in density. It was described by the Friedman solutions to general relativity. Over time, tiny differences in density started to grow and to clump together. This turned the smooth, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation dominated the universe and had a major impact on matter. This radiation prevented normal matter's density differences from growing and forming structures. If the universe only had normal matter, these differences would not have had enough time to evolve. They would not have become the galaxies and groups we see today. The key to solving this problem is dark matter, which is not affected by radiation. This allowed its density changes to grow, first creating gravity wells. These wells later helped normal matter to collapse into galaxies and other structures. The gravitational pull from dark matter acted like a magnet. It pulled in normal matter and sped up the formation of these large cosmic structures. A striking example of the impact of dark matter is the Bullet cluster. This was formed by the collision of two large galaxy clusters. What makes the Bullet cluster particularly interesting is the difference between where the mass of the cluster is located. This is according to gravitational lensing, the bending of light around massive objects, and where the visible matter is found. This difference is hard to explain with alternative gravity theories. These theories expect gravitational lensing to happen only around visible matter. However, the standard theory of dark matter can easily explain this. The visible gas in the clusters which interacts with light and other forms of radiation was slowed down. It was slowed and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, does not interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created the two separate lensing peaks, as was seen. In addition to dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can calculate how far away they are. This method has shown that the universe is expanding faster and faster. This is a phenomenon usually explained by dark energy. Baryon acoustic oscillation refers to the regular changes in the density of normal matter in the universe. These changes occurred on large scales in the early universe. These changes were caused by sound waves traveling through the hot, dense mix of photons and baryons. This was before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background radiation. As the universe expanded, dark matter and normal matter began to clump together, but the effect of the original changes weakened over time. However, we can still see a slight preference for galaxies to be separated by about 147 million light-years. This is a small but measurable sign of these early changes. This pattern was predicted in the 1990s and was confirmed in 2005. It was confirmed through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get a precise estimate of important cosmic values. These values include the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current main theory of cosmology. Large surveys of galaxy redshifts can help us to create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect. This is because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there is also a smaller effect from the galaxy's own motion, called its peculiar velocity. In general, superclusters, which are groups of many galaxies, are growing more slowly than the average expansion of the universe. This is because their gravity is pulling things together. On the other hand, voids, the vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies that are behind the supercluster appear to have a slightly lower redshift than was expected. This difference causes superclusters to look flattened along the line of sight. At the same time, voids look stretched. However, this effect is hard to notice in a single structure since we do not know its exact shape. Instead, scientists can see this effect by averaging data from many structures. The phenomenon was first predicted by Nick Kaiser in 1987. It was later confirmed in 2001 by the 2DF Galaxy Redshift survey. The results were matching what we expect from the lambda CDM model of the universe. In a related field of study, the Lyman alpha forest refers to the collection of absorption lines. These were found in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength. This wavelength is called the Lyman alpha transition. Observations of the Lyman alpha forest help astronomers test and improve cosmological models. The results match the findings from the WMAP data. Dark matter is often divided into three types: cold, warm, and hot. These names do not refer to a temperature. Instead, they describe how fast the particles were moving in the early universe. In simple terms, they show how far the particles traveled because of random movements. This was before the universe started expanding and slowing them down. This distance is called the free streaming length. The type of dark matter depends on how this FSL compares to the size of a protogalaxy. A protogalaxy is an early cosmic object that would later become a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it is called cold dark matter. If it is about the same size, it is warm dark matter. And if the FSL is much larger, it is hot dark matter. Some theories suggest a mix of these types. These were more popular in the middle of the 1990s, but they became less favored after the discovery of dark energy. The main idea behind the free streaming length is that after the Big Bang, the universe started with small differences in density. These were caused by tiny quantum changes at the smallest levels. As these particles move from denser areas to less dense ones, the fast expansion of the universe limited how far they could go. The faster particles, like those in hot dark matter, could travel further. They could do this before the universe expanded too much. The slower particles, such as those in cold dark matter, could not move as far. This means that the free streaming length sets a limit on the size of the structures that could form in the early universe. Hot dark matter would lead to the formation of large structures like superclusters. These would later break apart into galaxies. On the other hand, cold dark matter allows for smaller structures like galaxies to form first. Recent observations, especially deep field images of the universe, show something. Galaxies were formed first, followed by clusters and superclusters as the galaxies grouped together. This supports the idea that most of dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot make up most of dark matter. Since dark matter refers to any type of matter that interacts with visible matter mainly through gravity, it means something. Visible matter includes stars and planets. It means that dark matter might not be made of a completely new type of particle, but it could, in theory, include normal matter, like protons or neutrons. In fact, many objects familiar to astronomers fall into this category. These include planets' brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes. For example, when a black hole pulls in matter, it does not treat regular matter like protons differently from other kinds of matter. Once it is inside the event horizon, all matter is treated the same. These hard-to-detect objects are grouped together as macos. Some scientists once thought that macos made up most of dark matter, but this idea has since been mostly rejected. There is strong evidence that most of dark matter is not made of normal visible matter. First, if there were enough normal matter like gas or dust scattered around, we would see it when it is lit up by light from the stars. However, we do not see this kind of matter in the amounts that we would expect. Next, the Big Bang theory helps us to understand how the elements we see today were created. According to this theory, if there were more normal matter called baryons in the early universe, we would have seen more elements. Elements like helium, lithium, and other heavier elements. Based on what we observe, only about 4 to 5% of the universe's total mass is made of this normal matter. However, large studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further studies show that only a small portion of dark matter seems to be in the form of normal hidden objects. Objects like small planets or black holes called macos. Studies using the bending of light by gravity, gravitational microlensing, suggest that these objects cannot make up most of dark matter. This is because their masses fall in a range that rules out almost all possible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, show something important. These studies were done by missions like WMAP and Planck. They show that about 5/6 of the matter in the universe does not interact much with light or normal matter except through gravity. This suggests that dark matter is mostly invisible, and it can only be detected by its gravitational effects. If normal matter, called baryonic matter, does not make up most of dark matter, then dark matter must be made of something else, specifically a non-baryonic matter. There are two main possibilities for non-baryonic dark matter. These are new mysterious particles and ancient black holes from the early universe. Unlike normal matter, these non-regular particles do not help to create the elements formed during the Big Bang. This process was called Big Bang nucleosynthesis. Instead, we notice them only because of the gravitational effects they cause. Effects such as bending light, which is called weak lensing. Some types of dark matter can even interact with each other. This is self-interacting dark matter. Or they can interact with normal particles like WIMPs. These interactions might produce detectable signs such as gamma rays and neutrinos. Scientists could possibly observe these in a direct detection. There are many different candidates for dark matter, each with its own strengths and weaknesses. WIMPs do not have a strict definition, but they are generally thought of as basic particles that interact through gravity and possibly other weak forces like the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to normal particles. These particles would make up what is called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to destroy each other in a specific way. This fits with what would happen if they had masses around 100 giga-electron-volts and interacted through the electroweak force. This idea is often called the WIMP miracle. This is because it fits well with the predictions from supersymmetric theories which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a main candidate for dark matter. Researchers are working hard to find WIMPs by looking for the results of their destruction. Results like gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories. They do this by measuring their interactions with atomic nuclei, or by trying to make WIMPs in particle colliders like the Large Hadron Collider. However, in the early 2000s, TENS experiments did not find strong evidence for supersymmetry, and the LHC results made the simplest WIMP ideas less likely. Actions, another candidate for dark matter, are theoretical particles first proposed in 1978. They were proposed by Frank Wilczek and Steven Weinberg. These particles were first suggested to solve a problem in the theory of quantum chromodynamics. This theory explains how quarks and gluons interact. Actions are extremely light and weakly interact with other particles. This makes them a good candidate for dark matter. They could be made in the early universe and would still exist today. Their abundance depends on their mass. Actions are thought to be so light that they could help explain some of the small-scale problems in the lambda CDM model. This is the main cosmological model. The axion theory has gained attention in recent years, especially after WIMPs were not found. The axion's very low mass means that quantum effects could explain some of the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are thought to have been formed in the very early universe. They formed right after the Big Bang. During the period of rapid expansion called inflation, extremely dense areas of subatomic matter could have collapsed. They would have collapsed under their own gravity, creating black holes without needing a star to die. This is what happens with normal black holes. These black holes would exist before the first stars were formed, and they could have masses ranging from the tiny, even as small as atoms, to the very large, far beyond the usual stellar black holes. The idea of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly became popular as a possible explanation for dark matter. One of the advantages of primordial black holes as dark matter candidates is that the physics behind black holes is already well understood, general relativity, and the black holes themselves are already known to exist. However, making primordial black holes might need special conditions like an unusual cosmic inflation or theories that are beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers brought a renewed interest in primordial black holes, a renewed interest as a form of dark matter. Some of the black holes detected by these experiments had masses that seemed too large to be formed in the usual way, like from a collapsing star. This suggested that they could be primordial. However, a study looking for signs of gravitational lensing from intermediate mass black holes found no evidence. These were expected to be a form of dark matter, although some researchers suggest that this could be because of the assumptions about the black hole's mass. Further observations like those by the James Webb Space Telescope may give more clarity on this idea. Scientists once thought that very small black holes called primordial black holes might make up a large part of dark matter. However, the Voyager 1 spacecraft, which went beyond the Sun's influence, measured the flow of positrons and electrons, and it found something surprising. The number of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to make up dark matter.